So what I thought I could do is talk about why a credit system works. Lynn has discussed this emphasized this in his paper, but I think it's something that on a certain level has not really been fully understood. And you tend to think that, well, the difference between the credit system and the monetary system is that the credit system manages money better than a monetary system does. But there's an underlying principle as to why a credit system works, which actually, as Lynn points out in his papers, takes us into some very profound areas of science and epistemology and very fundamental questions about what the nature of the universe is. And and that's what I want to get into, at least as much as I can. And then we can see where we go from there. In a certain sense, I don't think it's too much of an exaggeration, although it might be a slight exaggeration, to say that the real difference between, or the issue that distinguishes a credit system in the way Lynn is talking about a credit system, not simply just a credit system in one country, but an international credit system, that differentiates that from anything that has existed in the last 150 years. And actually anything that's ever existed before, but in this form over the last 150 years, is that the credit system completely breaks with all notions that are typified by what has come to be known as the second law of thermodynamics. And most people don't really understand what the second law of thermodynamics is, and how bad it is. And that's because basically about little less than 150 years ago, the second law of thermodynamics was elevated to the central tenet of the official state religion of the British Empire. And since the British Empire has dominated world politics, including in the popular culture here in the United States to some extent, you have the predicates, or the substance of the second law of thermodynamics has been incorporated so much into the popular culture, scientific culture, artistic thinking, thinking in economics and so forth, that it very much the way the Aristotelian doctrines seeped into every one of the cults in the pantheonic system during the Roman Empire. The second law of thermodynamics is sort of tended to dominate the culture of the entire world and thinking over the last 150 years or so, and which is pretty amazing, since it's an actually very absurd idea in the way it was posed. But of course that shouldn't be so surprising, because there's been many times in history where whole cultures have been dominated for centuries by ideas which are absolutely absurd. And the one you're most familiar with, of course, is the period from roughly around the time of the murder of Archimedes by the Romans and Johannes Kepler, where for 1,500 years the culture of Europe was dominated by the concept, the Aristotelian cosmology that was expressed by the Ptolemaic system. And this was not just as you know from your history, the Ptolemaic system was not just a um, the Ptolemaic system was not simply something that had to do with astronomy, but it reflected a concept of man and the organization of society. And this has always been the way the way cultures work and the way politics works in cultures, where you have a reflexive relationship between the way people think about the way the universe works and the way they organize society. And in fact, in imperial cultures, they seek to define a organization of the physical universe that conforms with the necessary conditions to maintain an imperial culture, an imperial social organization, and vice versa. So there is no separation between science and politics, even though a lot of people think there is such a thing. And in fact, even the insistence that there is a separation between science and politics is itself demonstrative of the connection between science and politics, because you're actually asserting that there is a connection by denying that there is such a connection. And I think the easiest way to look at this, just paradigmatically, is the example I used in terms of the Ptolemaic system, which really is not Ptolemy's, because Ptolemy was a total fraud. In fact, all the data that Ptolemy used was faked and to fit into his idea. But the idea itself was not original to him. It's an old Babylonian myth, and it probably came even before the Babylonians, and it was revived by cultures that adopted an imperial system in reaction to the cultures that Lynn has talked about, that were these maritime cultures that were dominated by astronavigation. Because if you're a maritime culture and your culture is involved has understood certain basic principles that are associated with maritime cultures, which you can generally put under the umbrella of astrogation, you know from your experience, from your not from your sensory experience, but from your experience with working with the ideas on which your existence depends, that the nature of the universe is that it is everywhere changing. Because you're investigating at all times the way in which the motions of the heavenly bodies are changing and changing relative to each other, and how that your success of your mastery of these principles is dependent on recognizing that the motions are all being governed by a principle of change and are not in any way fixed whatsoever, right? And that, of course, reflects a view of man. You recognize in the heavens something about the nature of human beings, which is that mankind, human beings, have this characteristic that they are everywhere changing. Simply, in the most important way, by the succession of discoveries about the world around us and about ourselves, that human beings, that define really what a human personality is. Schiller makes this point, which I think is the most profound, succinct way to put it, which is that when you think about when you say, who am I? Right? Which is, of course, the most fundamental question a human being can ask. Who am I? Right? What is this thing that you're talking about, I? Is it a fixed thing? Is it some entity that you can actually identify as a fixed, unchanging quality? Well, there's an element of it which is unchanging, but there's nothing about it which isn't changing. Because when you think of your identity as a personality, the identity is as a capability to make discoveries, a capability to change. Because when you reflect on yourself, you realize that you're nothing but change, right? From your earliest memory to the present. You recognize yourself. You can't find a fixed identity of who you are, which is, of course, one of the things that is prevalent in our culture, which is so damaging, which is the attempt to try and impose on people a different view, which is why you get people saying stupid things like, well, I'm not this type of person. I'm not that type of person. I'm a science person. I'm an art person. I'm a feeling person. I'm a math person. You get people try and think of themselves as fixed. But when you actually think of who you are, it's a succession of discoveries. But Schiller points out that there's something, obviously, that is unchanging, that is asking the question. Because if you were everywhere changing, then every time you change, you're a new I. So, Schiller makes the point that there's this ironical relationship of what the human being is, which is what Plato might call an unchanging principle of change. So this is what you recognize from your own experience of thinking about the nature of a human being, and that corresponds to the principle of organization that even a primitive or an ancient maritime astronavigating culture is. So although we don't have we have limited archaeological and historical records. You do have things like the Vedic epics, you have legends, you have the stories of these cultures. Cultures which are associated with this kind of thinking, what we know of them, as we know of more recent cultures where we do have more extensive records, adopt forms of social organization which emphasize this principle of change as a form of social organization. Now, of course, the only time this was actually really achieved successfully was in the founding of the United States. And if you think about what Lynn has emphasized about the Declaration of Independence and the Constitution, that it's based on principles. And these are principles which are principles that reflect the principle of change as being the necessary organizing principle for the organization of society. So this was an accomplishment which goes back tens of thousands of years of a struggle for mankind to actually achieve that, the most perfect form yet of that type of organization of society. But as you know, that has been, despite the fact that there has been human progress over the last 10,000 years, this has been not the dominant form of culture where most people have lived in. Most people have lived in a form of culture which we would identify as an imperial culture. And under the imperial culture, no change is permitted. Society is organized so as to minimize change. And the idea is to accept by the change as introduced by the irrational will of the emperor. And if you look at the cosmology of imperial cultures, the Babylonian culture, the Roman, they all have this same characteristic to it. They attempt to explain the organization of the physical universe to reflect the imperial form of society. So you get the Ptolemaic system, where you have the earth at the center doesn't move. And this always conforms, these cosmologies always conform to sense perception. So the earth doesn't move. And as you get further away from the earth, you get, it's at the center of a big sphere, and the further away you get from the earth, the less things change. Everything on the earth is changing. Life, non-life, human life, It's all changing. And the further away you get from the Earth, the less things change, right? The sublunary sphere has a lot of change. The planets have more change. I mean, have less change. The fixed stars have still less change. And if you get beyond the fixed stars, where presumably the gods lie, there would be even less change. And therefore, and you see when you think about this concept, why Kuza put so much emphasis on his argument about the circle. Because his argument in Didacta Ignorantia is that in the visible domain, the circle and the center and the circumference are opposites, which is the Aristotelian cosmology. The Earth is as far away from heaven as you could possibly get. But then Kuza says, but in the infinite, the center and circumference are one. And you see this also reflected in Kepler's argument, even his criticism of the Pythagoreans in the Harmonies, where Kepler says that, you know, the Pythagoreans were right to say that the sun was the center of the world on one level, but we Christians have learned to reason better and know that the center is everywhere and nowhere. That this point that Kuza is making is in reality an excommunication of this Aristotelian idea and reasserting an idea which you see also reflected in the Platonic idea of in the Timaeus, that the physical universe itself is organized around a principle of change. You know, in the Timaeus, Plato gives the disclaimer, right? Okay, I'm going to describe the universe, a visual metaphor, but what I'm really describing is beyond words, beyond visual perceptions, and so forth. And he gives this image of a spherical universe. But his image of a spherical universe is completely different than this Aristotelian idea, in which the sphere is organized around this principle of no change being at the center. And in Plato's idea, the sphere is an image of something of what Einstein would later call finite yet unbounded. Now, so what you see is, when you look at, for example, from this standpoint, you can see, for example, the significance of Kepler's refutation of the existence of the equant. Because by proving that the equant doesn't exist, he's demonstrating something about the universe itself. It's that the universe doesn't just appear to be changing non-uniformly, but it is everywhere changing. It is as Kuza says it was. The physical universe itself conforms to the kind of universe that human beings, that reflect what human beings are. Now, and if you read Kepler thoroughly, as reading Kuza thoroughly, you see that Kepler was not unaware, and in fact emphasized, the significance of this for this idea, for what was happening to his society at the time. You look at the second introduction of the Mysterium, where he harkens back to the Delian problem, which is a similar issue. And says that what you're seeing in Kepler's lifetime is this clash between this imperial system, which is desperately trying to maintain this idea of no change, that the imperial system is the only system that man can organize because it reflects the way the physical universe is organized. And the imperial scientists are tasked with showing that the physical universe justifies, the organization of the physical universe justifies the imperial system. Right? And you see with Kepler and Kuza, it goes the other way. Now, because Kepler was so successful in what he did, as Lynn has pointed out, the oligarchy had to abandon this old Aristotelian idea, the form, but they didn't want to abandon the notion. And so you had this Sarpian liberalism come in, and a reintroduction of in effect, an ontological equant with the concept, Newton's concept of, and Galileo also had the same concept, not expressed the same way, but the same concept of absolute space and absolute time. Because if you have an absolute space and absolute time, now you have something which doesn't change, against which all changes occur. Right? So the no change is primary. The thing that doesn't change is primary. You can have change, but it's all changing relative to something which doesn't change, which is the power of the empire as embodied in the emperor. But it's not the emperor, right? The emperor is just a tool of the empire. It's the empire that doesn't change. And as we know, it's not even the seat of the empire doesn't change. It's not the seat of the empire isn't fixed, but the imperial system is fixed, right? So then, of course, Leibniz, you have this battle goes back and forth, and Leibniz, Gauss, Kessner, Riemann, they completely devastate this. And I'll go into more details about that in a minute. But then by the middle of the 19th century, this idea of that no change is the fundamental organizing principle of the universe gets reintroduced in a very, what might appear today to be a somewhat obscure route, but it really isn't when you actually get to the history, and that is with the introduction sort of contemporaneously by William Thomson, who later was renamed by Queen Victoria, first Baron Kelvin of Largs. And he was first Kelvin of Largs. So today they call him Lord Kelvin. Kelvin was the name of the river that ran by where he lived, and Largs was the little village. So they called him first Baron Kelvin of Largs. His real name was William Thomson, and he became Sir William Thomson, and then he became first Baron Kelvin of Largs, and sometimes you'll see him referred to as Lord Kelvin. And he studied, and then you had another guy who was responsible for formulating this idea, named Rudolf Clausius. This was both in the 1850s, 1860s. So, and they were studying thermodynamics, and I'll get into details a little bit on the question of thermodynamics in a minute. But just to sort of set the stage, what they said. So they were looking at this question of thermodynamic processes, basically heat. And heat, we'll talk a lot about this in a minute, but just to sort of make the point here, it's interesting when you look at the history of science that for most of man's existence, our knowledge of what we call heat was limited to really just cooking food and warming people, right? But it wasn't really until Leibniz's discovery of the principle of dynamics that you began to have the development for the first time of the use of heat as a means of power, increasing man's power over nature in the form of heat-powered machines. So at that time, the subject of the investigation of heat becomes a really central feature of scientific investigation. And so, which we'll talk a little bit more, we'll talk a lot about. But the heat, this question of heat, so therefore it was a big topic of discussion. As you know, at this time in Leibniz, Riemann's talking about in his fragments about the necessity to unify gravity, light, electricity, magnetism, and heat, which were the primary physical powers that man was gaining control over. And so the one of the things about heat that we'll get into more in a minute, but that people were that drew people's attention is that heat functioned differently than electricity, magnetism, gravity, or light. There were differences, but among all these things, which is why the question of coming up with a unified conception for light, gravity, electricity, magnetism, and heat was such a challenging question. But heat has a certain characteristic to it, which becomes recognizable when you're dealing with heat-powered machines, which is that the process of heat, the action of heat seems to go in one direction, from the warm to the cold. You don't have heat going from a cold body to a warm body. At least you don't see that happening experimentally. And we'll get into the more details of that in a second. But so Kelvin and Clausius were looking at about this, and which is in effect the way in which a heat power machine works. And this was investigated by particularly Lazare Carnot and Sadi Carnot. You've probably heard of the Carnot cycle, which was the result of the work of Sadi Carnot. Because the way Leibniz designed, based on Leibniz's design, you have the action of the power of a heat powered machine is you have heat flowing from a hot reservoir to a lower temperature, and that then is used to run a piston or lift a weight or something like that, right? So Sadi Carnot investigated this and developed the parameters for how to maximize the application of heat to the development of physical work. And this is what Clausius and Kelvin were sort of looking at. Now, but they did what good, loyal servants of the empire do, is they took something that is within the domain of sense perception and turned it into a universal principle. And the first statement was, but the first actually was Kelvin, and he wrote many strange books, but one he wrote was on the universal tendency in nature to the dissipation of mechanical energy. And in it, I'll just read you a quote. He says, there is at present in the material world a universal tendency to the dissipation of mechanical energy. Any restoration of mechanical energy without more than an equivalent of dissipation is impossible in inanimate material processes, and is probably never effected by means of organized matter, either endowed with vegetable life or subject to the will of an animated creature. Within a finite period of time past, the earth must have been, and within a finite period of time to come, the earth must again be, unfit for the habitation of man as at present constituted, unless operations have been or are to be performed which are impossible under the laws to which the known operations going on at present in the material world are subject. So he states, as a matter of principle, since the tendency is for heat to be dissipated from hot to cooler bodies, or to go from states of higher organization to lower organization, that there is the inevitability of what today people might call the heat death of the universe. He says, don't worry about that, because the universe, because mankind can count on the intervention from outside the universe of a creative principle, which will prevent this from happening. So if there's a creative principle in the universe, it's coming from outside. But otherwise, the universe is tending towards a new form of equant called no change, heat death. And it's, of course, Kelvin who you have the idea of absolute zero from. That you have that by extrapolating from this principle, that you can extrapolate down a state at which no more motion is possible and nothing moves, nothing changes. It's called absolute zero. That's what the Kelvin scale, Kelvin temperature scale comes from. Now, of course, the ironic thing is today we actually can get pretty close to that in the experimental apparatus. And you find that as you get closer and closer towards absolute zero, things actually change more. You get phenomena like superconductivity and superfluidity and so forth, where resistance to flow of electricity and fluid flows and so forth practically disappear. And you actually get more motion and more change and more nonlinearity as you get closer and closer. Now, Clausius, about 10 years later, was also trying to propagate the same thing, but being German, he tried to do it with a little more precision. And he wrote a book called The Mechanical Theory of Heat with its application of the steam engine into the physical properties of bodies, in which he basically sort of redid what Sadi Carnot had already established about the efficiency of heat-powered machines. And in that, he introduced a new word called entropy, because what he wanted to denote was that in the question of heat transfer, you have something which you don't have with respect to electricity, gravity, magnetism, or light, but you have this directionality. And so therefore, the principle that, which I'll go over in more detail in a little bit, of what sometimes is called the conservation of energy, which Leibniz is sort of a bastardization of the actual ontological argument that Leibniz makes in the Specimen Dynamicum about why you can't have a perpetual motion machine. But in the case of heat, you could have, if you didn't have unidirectionality, if heat could flow, you could have heat flowing from a warm body to a cold body, but if heat could flow from a cold body to a warm body, you could have a transfer of power which would lead to an increase in the potential, in your potential, without increasing you could create what Planck would later call perpetual motion of the second kind. And so he introduced the term entropy to denote a measure of this principle of directionality from states of higher organization to lower organization, in the context in the limited experimental context of heat-powered machines. And we'll get into more detail in a second on that, but just to set the stage. So he took the word entropy, he invented from taking the prefix "en," which in Greek means in, or internal, and is also the first letters of the word energy, energia. And the Greek word tropy. And tropy means transformation or change. It literally means change in Greek. So he invented the word entropy to denote a quantity which measures the internal change. And in a limited case of certain heat-powered machines, that nature of that change was from higher temperatures to lower temperatures. Okay? And so he said in this limited case, the entropy of the system, the entropy increases. Entropy sort of goes in the opposite. It increases as you get towards thermodynamic equilibrium, and low entropy means you have a greater potential for change. So another way to think about the limited concept of entropy is that it measures the relative potential for change. And the greater the entropy, the less potential for change. And the lower the entropy, the greater potential for change. Okay, just in the simple, limited way. Planck later put this concept on a more rigorous footing, which is what I'm referring to here. But that was not how, Clausius was not necessarily as precise as what I have. But despite the fact that he wasn't that precise, he was also crazy. And here's what he said at the very end of his paper, right? So he writes this whole paper about machines and so forth. And at the end he says, "For the present I will confine myself to the statement of one result. If for the entire universe, not a heat-powered machine, if for the entire universe we conceive the same magnitude to be determined consistently with due regard to all circumstances, which for a single body I have called entropy, and if at the same time we introduce the other and simpler concept of energy, we may express in the following manner the fundamental laws of the universe, which correspond to the two fundamental theorems of the mechanical theory of heat. 1, the energy of the universe is constant. 2, the entropy of the universe tends to a maximum. Period, the end. That's how he ended his book, right? So he writes his book about machines, where the thing is introduces nothing new about the nature of heat-powered machines than what Sadi Carnot had done, which was a crucial study in engineering that was necessary to determine what is the maximum capability to, how you create the maximum efficiency, the maximum power over heat, man's power over heat. And he comes to the end of this thing and he says, okay, now we can extend this to the entire universe. Completely arbitrary, right? And he declares authoritatively with the imperial decree, the energy of the universe is constant and the entropy of the universe tends to a maximum. Now there's no scientific basis for that at all, but from this point on, this becomes the form of the, as I said, the central tenet of the official state religion of the British Empire, which is that the universe is always tending towards states where the potential for change is decreasing. And therefore you have to organize society so as to minimize the potential for change, which is what the British Empire has been doing for the last 200 years, trying to minimize the potential for any change except change that's introduced from outside by the authority of the empire system itself. Now, and of course you can see how degenerate our culture has come, because for many generations this was introduced into the thinking by studies in schools about heat-powered machines. But it's come to my attention that with your generation, now this is introduced as a universal principle by the example of how your room gets messy. That no matter how much you clean up your room, it always tends to get more messy.
I used to discourage to not clean my room.
Yeah, this is what, right? So this doctrine, which used to be introduced into society, at least in the context of machines, if you were to try and do it today, doesn't work. So they just do it by the question of messy rooms. Now, before turning to the physics of this, we know, based on both our knowledge of science, but also most importantly what Lynn has discovered about the science of physical economy, that the universe does not conform to what Clausius says. It actually, when you look at the universe as a whole, it's going from lower states of organization and existence to higher states of organization and existence. Certainly that's demonstrable by the development of human beings. The chart that Lynn points to in terms of the secular increase in population. And that increase in population is affected by a increase in per capita power in and over the universe by mankind. And we know that that occurs through the development of the creative powers of human being, and that the development of those creative powers occurs through discoveries of principles of science and principles of mankind, artistic principles. And such discoveries advance the culture as a whole and the power of every individual in that, the potential power of every individual in that culture. So when you look at the action of mankind, you see that it's actually going in what Lynn has referred to as an anti-entropic direction, where the entropy is tending to be minimized. That at any moment in the development of the human society, the successful societies are those which are increasing the potential for change. And of course, the most successful society in terms of increasing the potential for change is what is the credit system and the constitutional system of the American Republic. Right? If you want to characterize what the American constitutional system does, it increases the potential for change. But this is something that in the American culture is made explicit. But it is an inexorable characteristic of mankind. How else can you account for the fact that for most of human existence, most people have had their potential minimized by living in bad cultures? Even in the United States, most of the time, most of our presidents and politicians and political leaders, and most of the time, most of our people have been pretty bad. And yet you've had progress. So the inexorable direction of mankind is not towards an imperial, is not to maximize entropy, but in fact you see the opposite, which is that every time you try and maximize entropy, you produce exactly the opposite result, as is witnessed today. If you think about the monetary system as it morphed into this insanity called globalization with derivatives and everything else, this is like the ultimate attempt to try and maximize entropy in the world. That's what derivatives do. They minimize the risk, right? You try to minimize all dramatic, you try to tamp down swings in the business cycle and in monetary values and everything else by spreading the risk and creating these bubbles of derivatives and all these other exotic financial instruments that are, ironically enough, developed using the mathematics of the quantum mechanics, which itself is based on the second law of thermodynamics. And it's produced exactly the opposite result. Here we are at a point where you've had successful implementation of a system that maximizes entropy. And it has created a condition where the potential for change is at a maximum. For good or for ill, right? How it's going to change, whether it's going to be the change in a credit system or a dark age, that hasn't been determined. But even if it goes in a dark age, that in a sense tends towards minimizing the entropy because it will destroy this bad system that will enable us to rebuild something new. And it's, of course, is the point they made in the Dark Ages video, that you couldn't have had the Renaissance if you hadn't had a global collapse of the oligarchy, so that it was so weakened that a new system could come into existence. In the same way the American founding fathers took advantage of the weakness of the European oligarchy at the time and struck to create the United States. So we have to take, it's not guaranteed that the oligarchy right now is weak. So if we take this moment, we can shift it. But the point I'm focused on is that you see that there is a characteristic, certainly from this standpoint, in the development in the nature of human beings, of human society, that the tendency is to minimize entropy, not maximize it. And any attempt to maximize entropy actually produces the opposite result. Now we know from, however, from both Lin and also from the experimental evidence of Vernadsky that and this is also the view that of Kepler, of Kuhn, of Plato, of Riemann, and so forth, that this characteristic is not a characteristic that is limited to human beings. That is, you don't have a situation, to put it in our modern language, where the characteristic of humanity is anti-entropic, while the universe as a whole is entropic. Right? And this is very important because one of the sophistries is, okay, yeah, you can say that about people, but the physical universe is governed by the second law of thermodynamics. And therefore, any anti-entropic tendency of mankind, even though it's necessary for human development, even though human beings will inexorably organize higher states of organization and existence, everything they do will ultimately be futile because the universe as a whole is pushing in the other direction, anti-entropically, right? So again, you've introduced a type of equant, right? You say, well, yeah, okay, you can observe non-uniform motion of the planets, but there's some equant somewhere that uniformizes. So yeah, mankind can do all this changing and development, but ultimately it will lead to catastrophe. Isn't this the basis of underlying the argument of global warming? That all efforts to improve, that this inexorable necessary characteristic of mankind to increase his power over nature will ultimately lead to this catastrophe. Right? Of course, but as we know, the catastrophe doesn't exist. That's just an artificial construction that has to be imposed on the physical universe itself. So therefore, when you look at this anti-entropic characteristic that we see with mankind, it's not something that is just isolated to human beings, but it is characteristic of life, and it's characteristic of non-living matter as well. I think, to put it in the most profound way that Lin refers to it, is that the universe is ontologically creative. That it's always striving towards higher states of organization of existence in all domains, living, lithosphere, biosphere, noosphere, and the physical economy. And Berlin differentiated this fourth domain of human interaction. And so this what Clausius's fraud is not just a fraud on his face, but it's a fraud because the actual characteristic of the universe, the entire universe, is anti-entropic. And you see this in the physical world in terms of phenomena like the Crab Nebula, or the development of galaxies, and supernova, and all these astrophysical phenomena in which new states of organization and existence are being created. You see it in the Keplerian idea of the creation of the solar system, where out of a spinning plasma disk, you get the development of the solar system harmonically organized with the capability with an Earth which sustains life and human life, from which human beings now go out beyond the Earth into the solar system and beyond. So you actually, so the characteristic of all parts of the physical universe is anti-entropic. Now, it's absolutely necessary in terms of to do anything good that you speak truthfully and boldly about evil. Hence, it's appropriate to use the term anti-entropy to describe the process, even though it tends to be somewhat confusing to some people at some times, because you're saying the actual positive direction of the universe is to go against something which doesn't exist in the universe. Right? But because this concept of entropy is so embedded in our culture, it's necessary and appropriate to root that out. So the term anti-entropy is necessary. I suggest that we could also introduce a new term which represents this universal characteristic of pervasive creativity. And I suggest the term we use is dunotropy, which I think is appropriate because it comes from the Greek word change, tropy, and the Greek word power, dunamis. What dunotropy expresses is the idea, is the principle of dynamic transformation as opposed to an internal transformation. It's a dynamic transformation in which you have a process which increases the potential for you have a tendency to maximize the potential for change. And such a universe that is dunotropic could only exist in the form that Einstein described as being finite and unbounded. And I can explain that in a little bit. And I'm currently working on elaborating this idea and the means by which you would express such a concept, which would be a Riemannian-type tensor, but it would be not a mathematical construction of a Riemannian-type tensor. It would have to at the same time preserve the quality of precise ambiguity that is necessary to capture the principle of creativity. Now, in constructing such a concept, you can already see you have to start from the highest standpoint, first of all, which is Lin's work on physical economy. Because this has advanced our knowledge of this nature, this characteristic of the universe, beyond what anybody had ever done. So you don't build it up from the bottom. We don't have to. One of the good things about an anti-entropic universe is you don't have to recreate the universe every time, because the universe is always creating itself new. So, but if you start from the most advanced standpoint and go back, you can see the roots of a lot of these ideas already. As I said, in Plato, you can see it in Cusa, you can see it in Kepler, you can see it in Leibniz, Fermat, Riemann, Gauss, and so forth. And also in Einstein. And to a certain degree in Max Planck, although he's somewhat more like Gauss. He's a little bit more reluctant to, for reasons I'll explain. But you can't. None of these guys really, except to some degree, really considered the matter the way Lin did. Now, of course, and it's always easy when you look at a discovery to look at all the predecessors and to say, well, the predecessors really had the idea. That's in hindsight. But that's a mistake, because Lin has actually introduced something new, which you won't find in Vernadsky or Einstein or Riemann or Leibniz or Plato at all. A new insight about this, which makes it possible, without which I don't think it's possible. I know it's not possible, but it's an insight which makes it possible to actually elaborate and establish this concept of anti-entropic potential in a way that had never been done before. And Lynn has laid the basis. Lynn has developed the fundamentals of that. So that's the place to start. And from that standpoint, you can go back and begin to look at this period over the last 150 years. And because you've had this ironic development over the last 150 years. You had, from the Renaissance, from Kepler really through this period, at the end of the 19th century, you had a tremendous amount of progress in fundamental ontological scientific ideas. But then beginning around the turn of this century, you had a complete reversal of that, largely because of this dominance of this attempt to reinstitute the second law of thermodynamics, or make that the central tenet. And so you've had the ironic situation where you've had a lot of developments in the application of the fundamental ideas which were made in earlier times. But the knowledge of the fundamental ideas has regressed over the last 100 years. And that regression is reflected in the fact that the 20th century has been, by and large, with the exception of what Roosevelt did, a pretty bad century for mankind. So you've had this ironic situation, which in a certain sense is similar to the situation that Kepler found himself in, where you had this tremendous flowering of ideas that happened around the Renaissance. And then you had the reaction beginning in 1492 and 150 years of religious warfare. But yet the effects of the discoveries of the Renaissance were continuing to produce improvements in technology. But the culture and the ideas and the power of science was going backwards, as Kepler's point about Ptolemy, Copernicus, and Tycho Brahe is exemplary. So Kepler reconceptualized all the discoveries that had happened from the from the superior standpoint, and produce the breakthrough. So what we have to do is go back and look at these these discoveries, which really occur at the end of the 20th century, the end of the 19th century, beginning of the 20th century, because the science which has been interpreting them over the years has been really bad. You know this from your own experience. Almost every scientist, even creative scientists, have no idea how they make their discoveries. And in fact, they think they base their discoveries on the wrong science. You know, you talk to space scientists, and they'll tell you, we use Newton's laws to send a man to the moon. And they don't use Newton's laws to send a man to the moon. They use their insights, their ingenuity, their creative thinking. And they then screw it up when they have to explain it in mathematical terms. But the first thing any scientist learns when he or she tries to do something effective is to throw out the mathematics and to use their brain. So that's what we have to do with physical science, and that, I think, gets to the point where we can begin to look at what I think is a crucial turning point, which is the work of Planck and Einstein in this regard. Now, the ironic thing is that had their discoveries been understood in the way I think they intended, today we would be thinking about Clausius like you do, those guys in ancient Persia who thought that the earth moved on the back of a turtle. I mean, it would just be one of those screwball ideas, that some jerk came up with that we all laugh at, right? But what happened is that Einstein and Planck made these discoveries, and then they got hit with a backlash which was, more intense than anything anybody could possibly imagine. They were hit with a real, the full force of the imperial powers. And in fact, that's where, when you understand what they were hit with, you begin to appreciate, first of all, a little bit more the integrity of a man like Planck, and even more the irreverence and courage of Einstein. Because when you see what they were up with, and that of course gets us to this ironic situation where what Einstein today should be most praised for is the thing he's the most criticized for, which is his stubborn refusal to capitulate to this second law of thermodynamics. And yet it's the thing he's criticized the most for. And meanwhile, it's the point that Schiller makes about Wallenstein in a different context, however, that the enemies write the history. His enemies have written his history up till now. So we got to write the real history of what Einstein actually did. So that means we got to understand it. So let me just introduce one aspect of what they did, which will be sufficient to make the point concrete that I've just made in general, and lay the basis for some future discussions. And that is that the actual nature of the discovery of both Planck and Einstein, Planck in 1900 and Einstein in 1905, of what became known as quantized effects. Now this arises out of what Riemann was reflecting in his fragments, where he's talking about the necessity to come up with a unified idea of light, electricity, magnetism, and heat, and gravity. Which, when Riemann says that, he's really reflecting also what Leibniz was talking about in all his works, and also what Kuza's referring to as well. But Leibniz did not deal too much with electricity and heat. He dealt somewhat with magnetism and gravitation. But here again, the issue posed here again reflects this conflict between two views of the universe, the imperial and the human. And this is another characteristic. One characteristic of imperial cultures, the imperial versus human, is this idea of whether change exists or whether no change is primary. This, of course, is the subject of even as far back as Plato's dialogue. Another is a false separation between so-called material objects and immaterial objects, and immaterial substances. That is an essential characteristic of imperial doctrine, imperial religious doctrine, that you have a separation between the material and the spiritual. That's the other thing that happens, right? The earth is all bodies, heavy. That's why it's at the center. Material. All the material in the universe sort of goes towards the earth. And as you get further and further away, things get lighter and less material. Okay? And this reflects this bestial view of man, right? That man really is essentially our biological creature. We're limited to our sense perceptions. Our interaction with the world is through our sense perceptions. And our existence is limited to our biological existence. We're born and we die. And that's it. The spiritual part of man is eternally separated from the material. Right? And you see this dogma running throughout imperial societies, right? But if you think about what Plato is discussing, what Kuhn is discussing, what Lynn talks about from the standpoint of the immortality of the soul, That's not the nature of mankind. You don't have a separation between, you have immaterial. There's something about man which is not material. Ideas are not material. Lynn has emphasized, how much does an idea weigh? What's the electron volts of an idea? There's no material determination of ideas, but yet the ideas are what determines the characteristic. They have a material effect. Ideas, by the way they change the way people think, which is what ideas do. Ideas don't directly change, they don't directly produce physical effects, but ideas change ideas. And by changing ideas, you change man's relationship to nature, and that produces a physical effect. But you do not have any ideas that don't arise or exist in a human being who has a physical existence. Even if you're dead. You can't think of an idea without associating it with a real human being, even if you don't know their name. You have to, you think of the Pythagorean theorem, you don't know Pythagoras. What do you know about Pythagoras? Nothing, right? But you have an idea. Okay, he's a guy, he was born around a certain time, he lived for a certain period of time, he ate, he slept, he did everything, he had a body. And where are his ideas today? Are they out in the ether somewhere? And they go into our heads from the ether? No, they arise in us, in real living human beings. If there aren't human beings who are developing ideas, the ideas, this is the location of the ideas. So you don't have a separation between ideas and the physical person. These things are connected, and ironically, as Schiller, Lynn, Kuza, Leibniz, everybody thinks about this, comes to realize that it's the mortality of the physical body, but the immortality of this, which guarantee, or in a certain sense, is essential towards the immortality of the soul. You can't, if you were, as Swift points out, if you were to not die, your soul would not be immortal if your physical body didn't die. So this the central doctrine is of the imperial doctrine is to have this separation between the material and the immaterial, and this is reflected in the scientific ideas of trying to introduce into the physical world things which are immaterial, like forces that act at a distance, and things that are material which are susceptible of being known through sense perception. Right? Versus the Keplerian idea, or the Platonic idea of physical science, where Kepler identifies the principle of gravitation as a species. That's the word he uses, right? Which is the Latin equivalent of the Greek word idea. Now, it's an idea. It's not a human idea. It's not a willful idea. It lacks a physical idea lacks the quality of the ideas of a living organism or the potential ideas of a human being. But it's nevertheless an idea in the sense that it's an immaterial power which is actually determining physical effects. It's not separate from the physical effects. You don't have gravity without bodies. You don't, as Gauss points out, you don't have magnetism without a magnet. Magnetism is immaterial, but you won't find it anywhere except with the magnet. Where's the magnetism? You have an iron bar, it's not magnetic. You magnetize it, it weighs the same. You've not had an increase in matter. But yet you have a new effect, an immaterial effect. Where's that immaterial effect? Can you have it without the magnet? So even in the physical world, you don't have a separation between so-called material objects and physical ideas or physical principles. And it's the same thing with life. With living organisms, now you have a new principle, and that new principle of life is immaterial. Where does it exist? When the organism dies, does it lose weight? Does it destroy the matter? Is there any less matter in a recently deceased organism than the organism that was just alive? There's no less matter. But some principle has changed, and that principle of life not only organizes the matter, but it organizes the physical ideas that is organizing the matter, as we're now beginning to discover, as Vernadsky talks about, and as we're being, do the experimental work, that electricity, magnetism, gravitation are different with respect to living when they're under the control of life. So life is a type of idea which has the power to organize both matter, material and immaterial parts of the universe in a way that those material and immaterial forces and matter cannot themselves, right? So it's the so you get this was the big debate. What you see is Riemann is talking about in his fragments a lot about. This is one of the questions he's getting at, right? The interaction between material and immaterial as being the place where you find the actual principles. And this idea, that's why he seeks the solutions for this in looking at human thought. His investigation of Geistesmasse. Now, so when you look at the experimental work, in a sense, all good experimental work, you're looking at the interaction to try and discover where the principle is. How do these interactions work? And as Linz emphasized with respect to Kepler, the ironical thing is that the interaction enters into the domain of sense perception. But the principle that's governing the interaction is not in the domain of sense perception. Right? And so so you have to go beyond the domain of sense perception to be able to get to the principle. And the way to do that is to look for a contradiction between two different senses that are investigating the same interaction. As in the case of Kepler, where he uses the sight and sound, the way in which the interaction of gravitation presents itself with respect to sight and sound, and what is the contradiction you get between them. Now, in the case of heat, you get something really interesting, which is a contradiction between touch and sight. We talk a lot about sight and sound, but touch is a very important element of the sense perception. Because you wouldn't even know that heat exists if you didn't have a sense of touch, any more than you would know that light exists if you don't have your eyes. But you know that light is independent of your eyes. So this interaction, this characteristic of light and heat, became a real central focus for scientific investigation in the middle of the 19th century. Not beyond the capability of the development of heat-powered machines, but because it was recognized that in this interaction, you're actually getting at something universal. Now and this came to a concentrated point in the experimental work that Planck was investigating, which was brought to his attention by his mentor, a guy named Gustav Kirchhoff. Planck, he was not Planck's teacher. Planck came from a family of prominent lawyers and theologians. It's interesting, right? Riemann, similar background. And he was a classical pianist, and his first interest was to make a career either as a pianist or as a philologist, and as Riemann and Gauss, because what he was primarily interested in was ideas.
Mm-hmm.
And his family moved to Munich, and he went to the University of Munich, and he got interested in some of these questions, physical questions, so he went to his professor and asked the advice of taking up a career in physics. And his professor said, don't bother. First of all, there's no jobs. And secondly, with the discovery of the second law of thermodynamics, there's nothing more to be discovered in physics. We know everything there is to know. And so the best you're going to hope to do in your career is find some minor new application. So Planck, but he didn't think he had what it took to be a classical pianist, although he never stopped playing the piano. And in fact, his house in Berlin became sort of the primary venue for the Musikabends of the Prussian Academy of Sciences, which included in the Musikabends some of the same people who were as young men in the Musikabends in Dirichlet's house and Rebecca Mendelssohn in Göttingen. One in particular I know of is Johann Joachim, who was the violinist that Brahms wrote the violin concerto for. And Joachim was a young man teaching violin at Göttingen, and Dirichlet and Rebecca Mendelssohn were there. And Brahms came through Göttingen, that's where he met him. And then later, as an old man, Joachim shows up in Planck's house at the Musikabends, where Einstein is playing the violin with Planck and also others. So it just gives you the taste of what kind of person you're dealing with here. Okay. So he goes to Berlin, and Kirchhoff had honed this question about light and heat down to a very interesting phenomenon. First of all, he looked at the fact that you get an interesting relationship in the interaction between light and heat and material bodies. That light, material bodies both absorb and emit light. They absorb light, light falls on the body, and the body absorbs light. And as a result, the body becomes warmer. You know, you take a piece of metal and you go out put it in the sun and it'll get hot. Right? What's making it hot? Where's the heat? Well, you say, well, there's fire in the sun. But is that heat being transported through space all the way down to the metal? Where's the heat coming from? And conversely, when you heat a material body, it emits light. You're most familiar with this with a stove. You turn on a stove and it starts to warm up, and as it warms up, it starts to glow red, starts to emit light. So, to make a long story short, I mean, the details are quite fascinating on this, but what Kirchhoff had demonstrated was several things of extreme importance. One was that the ability of a material body to absorb heat, to absorb light, was exactly equal to its ability to emit light. So a body that and And secondly, that the rate, the manner in which a body absorbed light and emitted light was dependent only on the temperature of the body and not on the material.
What was the first thing you said again?
That
Give an
the,
example.
yeah, like you have well, let me just add one other thing in this, okay? Just to that will make it clear. I was going to do it afterwards, but I think the confusion comes from not adding the following thing. First, we had the first, at the same time, there were in the beginning of the 19th century, some major breakthroughs in the discovery on what is the nature of light. Which is also interesting that people didn't really know what light was. Kepler really made the first modern breakthrough. The Greeks really didn't have much, at least they didn't discuss much of a sense of what light is. But Kepler's optics are the first real breakthrough in the discovery of light. Kepler's the first one to really specify that the reason why we see objects is we're seeing the light reflected from those objects to our eyes. Prior to that, it was believed that the light emanated from our eyes to the object. But Kepler was the first one to describe that. Matt, could you get me a cup of water too? Some
Water or apple cider?
No, water, just so my voice doesn't dry out.
Yep.
So the question is, what is the nature of light, right? And Newton had this idea that light was a stream of particles that was emitted from the, like when the sun had light, there was a stream of particles coming down at it. But the experimental evidence, all kinds of experimental evidence, including refraction, are refuted by that theory of light. And you know Huygens had the idea of light was a wave. But because of the preeminence of Newton as the high priest of Babylonian intelligence, the corpuscular theory tended to dominate. Actually, the first wave theory comes from Leonardo da Vinci, that light behaved like a wave, like a water wave. And in the beginning of the 19th century, particularly, there were two guys, Thomas Young in England and Augustin Fresnel in France, who did a series of experiments which you can replicate, which are quite fun to do, that show that when light interacts with a material substance, that the light behaves in the same way a wave, a water wave, or a sound wave acts with respect to a material substance. You could do these two-slit experiments where if the two slits are close enough together, you can shine a light through the two slits, and on the wall will be diffraction patterns, which will be the same as if you had a water wave going through two slits. It would break up into these types of patterns. And Fresnel did a whole bunch of other experiments, which are all quite doable and extremely fun, which demonstrate that when light interacts with material bodies, it behaves like a wave. Now, and Fresnel had done a lot of these, and also had shown two things: that when you shine light through a prism, it breaks it up into different colors. And if you then take each color and determine the wave characteristics of each color, you can actually measure. He did this with, instruments which are at your disposal. He actually measured that the change in color represented a change in the wavelength of the waves of the light. So that red light was of the longer wavelength, going up to the violet would be increasing the wavelength of the light. And he also found that when you put it through a prism, you find that there's heat. You take the light through the prism, you find that you can heat an object by having it fall in the part of the rainbow where there's no color at all, on the outside of the red, and it still has heat. So that led him to hypothesize the existence of a connection between radiant heat and what he called infrared spectrum, which is not visible to the eye. So that made that was a demonstration that when you're dealing with light, you're dealing with a something which was just a section of a visible part of something which goes beyond the domain of sense perception.
Oh, you're saying that there was heat even in the parts that were invisible.
Right. Yeah, in the lower than red. Okay.
Is the other one on the other end of the spectrum, the ultraviolet?
No, yeah, the ultraviolet, but you don't get that very, anyway. So the interesting thing is, so you see all this experimental evidence poses a whole bunch of questions. Like, for example, if light is a wave, what's it propagating through?
I was going to ask that.
Right, that's the question, right? Oh, first question, what's it propagating through? Because, a wave doesn't move. As Da Vinci did the experiments with water waves, you put a cork on the water and the cork goes up and down, right? What's the medium? Sound. If I'm sure you all did that experiment when you were kids. You put the alarm clock in a bell jar and you suck out the air and you don't hear the alarm. Then you lift the air and the alarm's going, right? So that you need air for sound, you need water for water waves. So what's the light propagating through? Well, if it's propagating through a substance, which they call the ether, this substance has to be so thin that every object, material object, can pass through it without resistance. And it has to, but it also has to be really, really, really stiff, because it was Ole Romer had already shown that light moved at a finite velocity, and Kohlrausch, who was one of Riemann's mentors, and Wilhelm Weber had measured the actual speed of light to be 186,000 miles per second, or equivalent of that. Yeah. So if for a wave to travel that fast through some medium, the medium has to be really stiff, right? So that you get a little impulse here will send that wave down through the medium, right?
Mm-hmm.
And of course, this is not a flat medium. You're not talking about the surface of the water. You're talking about something which is in 3 dimensions and is everywhere, okay? And has to be so thin. So obviously, the existence of such a thing is hard to. It's necessary to imagine if light is a wave, and the evidence seems to indicate that light is a wave. But it's almost impossible to imagine how such a thing would exist or how you would detect it. Now, just parenthetically, Einstein later rejected the idea that such a thing could exist. Why? Because if such a thing existed, then it would be at absolute rest to everything else, because it would have to be everywhere. So it couldn't move, right?
The ether?
The ether would have to be everywhere, right? So it couldn't move. So everything would be moving relative to the ether. So Einstein rejected it for the same reason Kepler rejected the idea of the equant. That you can't have a universe which is based on change and have something in it which doesn't change.
That's what I was going to ask you about the light going through the medium, because I mean, if you did think of it as a wave in the way that water does, you're assuming that whatever it's going through is just it's going through that. In other words, the change is.
That's not changing. The change is the vibrations in this ether.
Yeah, but that assumes what the state of space.
Yeah, that assumes an absolute. That actually reintroduces Newton's idea of absolute space as a physical existence. Newton put absolute space as some thought, that absolute space exists and everything moves. It's a sensorium of God. That's what he called it, absolute space. But now if you got this ether, now all of a sudden this mystical idea becomes a physical existence. That it's like the equant again. And that's what Einstein rejected on that grounds. Now, around the same time, Michelson and Morley did this famous experiment which demonstrated that the ether doesn't exist. But Einstein knew of that experiment, but discounted it. In all his writings, he said it was not the determinative question. The determinative question in his mind was that you couldn't have something that was at absolute rest in the universe. So that's just an aside, a later aside. Of course, it raises a question: if the ether doesn't exist and light still behaves as a wave, which it does,
Yeah.
what is it? Okay, so that's an unanswered question to this day.
Oh, yeah.
Absolutely. Lynn has posed the only competent concept for this, which is the idea that light is actually a self-propagating medium. That light is the medium through which it propagates. I'll get into that later. That is not such a far-fetched idea. Okay, so now the second problem that comes up, in addition to this question of the ether, is, okay, if it's an oscillation in the ether, what causes the oscillation to begin? I mean, the way you get a sound oscillation is you vibrate a string or your vocal cords, or you create, and it's not just the string. The string produces the sound because the string vibrates, but then the bridge and the sound post and the whole construction of the instrument produce a very complex set of transformations of the air, right?
He said, how do you get the light propagation to begin?
Yeah, what causes the... You don't... Light like magnetism, electricity, gravity, heat, doesn't exist except out of luminous bodies. You don't have light without some source of the light. So what in the material body is setting this ether in motion to produce this vibration which you call light? And when the light hits a body, what causes the body to... What in the body starts oscillating? If it's going to absorb the light, then something in the body has to start oscillating as a result of being hit with the light. Just like, when you're in the ocean, and a wave comes by and you're sitting there in the ocean, you start oscillating. You start going up and down with the waves, right? So if a light is hitting a body and it's oscillating, then there has to be some oscillation inside the material object.
The other thing, Kepler, I forget where he says it, but with light, you don't see it as it's traveling through space. You see it
Right.
once it interacts with the body,
Exactly.
which is interesting also.
Yes, because Kepler in Kepler's mind, this idea of material versus immaterial are not two separate things.
Yeah.
It's a single universe in which matter and immaterial things. Matter is relative, as Einstein later showed.
Kepler used that analogy. He used that as an analogy for gravity. Right?
Light, yes, and magnetism.
And then Lynn used that analogy recently for cognition. Said it's a principle which exists as potential, but it requires a material
Absolutely.
that will carry it, will
Right.
receive it.
That's what I was just talking about. Yeah,
Yeah, right.
Absolutely. You don't have this idea of a separation between material substances and immaterial substances are two separate things, but they don't exist independent of each other. They only exist as an interaction. You only have one universe. You don't have life and non-life and cognition existing in the universe separately. There's no place in the universe where all three principles are not existing. But the principle of organization is different in different places. The relationship is different in different places. But if you can't get life from non-life, then you can't say that you had a universe in which life didn't exist. Where did it come from then? It had to have been there from the beginning. And cognition had to be there from the beginning as a principle.
It's the medium that changes.
It's the interaction, but the medium that's changing is not a medium that is absent singularities. We'll get into that. This is where you start to see how when you start to look at these things, that what you're ultimately where you have to get to understand this, is you have to get at the questions Riemann was dealing with in his discussion of hypergeometries and the P function. That's where you have to get, that's what Riemann was actually looking at. And when you look at the physical world, how this applies in physics, or also how it applies in life, and how it applies in human interaction. Look, let's, sometimes you have to take things out of order, but let's take this point directly, okay? What is a creative discovery? How does it work? Take the case of the Meno dialogue, which is one of the best little descriptions of how this works. Right? The slave boy is given the problem, and the slave boy responds to the Socrates doesn't tell him anything, just asks questions, right? He just asks questions. And the reaction of the slave boy to these questions is the same reaction that you've had when you were first presented with this, and the same reaction that everybody you tried to teach how to double the square root had. They all do exactly the same thing, right? Whether they've seen it before or not, right? You draw the square, the first thing they do is double the side, and they get a square which is 4 times as big. And the next thing they do is they cut the side in half, and they get the right size but the wrong shape. And now they've got the problem all set up, which they did all themselves, right? And then they sit there and look at it, and if you're a good teacher, you don't give them the answer, and you let them sweat and scream, and then finally they come up with the discovery. And when they come up with the discovery, what's happened, right? What's the difference between knowing the answer and not knowing the answer? Having the discovery and not having the discovery, right? It's a discontinuity, right? Now there's a discontinuous change, which is not a discontinuity in which you know the answer. The answer is not the discontinuity. The discontinuity is the change in the way the slave boy thinks about himself, having made the discovery. Because the slave boy, and any slave who goes through this process, recognizes something about themselves, which is that they're not a slave. Right? It's like, I always use the example of Frederick Douglass. When did he say, if you read his autobiography, when does he get his freedom? When he decides to learn to read. Not when he learns to read, when he decides to learn to read. Because once he decides to learn to read, he has a different identity. And it's irreversible. He can't go back. That's why even if at that point he said, I'm not going to learn to read and I'm going to be a good slave, he's a marked man. Right? And the same thing with the slave boy. Once you make a discovery, it's an irreversible process. You can't go back to your previous mentality. But that discontinuity occurs as part of a continuous act of thinking. Here, I'll read you something which is quite nice, actually, that Einstein wrote in his autobiography, his autobiographical notes. He says, "What precisely is thinking? When on the reception of sense perception, memory pictures emerge, this is not yet thinking. And when such pictures form sequences, each member of which calls forth another, that too is not yet thinking. When, however, a certain picture turns up in many such sequences, in that it connects sequences in themselves unrelated to each other, such an element becomes a tool, a concept. I think that the transition from free association or dreaming to thinking is characterized by the more or less preeminent role played by the concept. It is by no means necessary that a concept be tied to a sensorily cognizable and reproducible sign, word. But when this is the case, then thinking becomes thereby capable of being communicated. I have no doubt that our thinking goes on for the most part without the use of signs or words, and beyond that to a considerable degree unconsciously. For how otherwise should it happen that sometimes we wonder, quite spontaneously, about some experience. This wondering appears to occur when an experience comes into conflict with a world of concepts already sufficiently fixed within us. Yeah.
Could you go back a couple of lines?
Yeah, okay. I have no doubt that our thinking goes on for the most part without use of signs, words, he has in parentheses, and beyond that to a considerable degree unconsciously. For how otherwise should it happen that sometimes we wonder quite spontaneously about some experience? This wondering appears to occur when an experience comes into conflict with a world of concepts already sufficiently fixed within us. Whenever such a conflict is experienced sharply and intensively, it reacts back upon our world of thought in a decisive way. So you have a continuous act of wondering. That wondering is going on in your mind, in the mind of the slave boy, in the mind of the of anybody, and that's where the discovery is occurring. That's where the work is being done. And then the discovery happens and you get a change, right? That discontinuity is introduced into what Einstein calls here this world of concepts that become sufficiently fixed within us. And then you get a conflict, which sets this process in motion again. So you see that the form of the generation of creative ideas is precisely a form of a process which is a continuous act generating discontinuities, which is irreversible. It goes in only one direction. And every new discontinuity creates a greater potential for further discoveries. Right? And that has to be the form by which this creative principle exists in living and non-living parts of the universe, the living parts of the universe that are not human and the non-living. That's what's happening. You get. It's not that you have matter and immaterial substances, but you have a continuous act of creation, which is organizing itself to higher states of organization and existence, which produces a changing relationship in states of matter. That ultimately is what you're looking at in this question, that's the ultimate solution to these kinds of paradoxes that occur when you look at this interaction of light and heat with material substances. And that's why Planck was interested in this question, because it raises these conflicts, the experiences within the domain of sense perception, or the extended domain of sense perception of the instrumentation, raises this conflict. What kind of world are we looking at? And these kinds of things come up. Now, the other problem you get with the heat is that the heat goes in one direction. It goes from a hotter body to a colder body, which you don't get with light. A body can absorb light and emit light. But with heat, it seems to go in only one direction. So there's all kinds of problems that are posed with this, right? One problem is, okay, we address. In order for light to be a wave, you seem to need some material, some fluid by which it travels. Well, for a while they thought that's the way heat worked. That heat was an actual fluid, a different fluid, called a caloric. This is where the caloric theory of heat comes from. And that this fluid, caloric, would flow from, it's in a body. If a body was warm, it had more of this fluid in it. And when the heat flowed from a hot body to a cold body, the caloric fluid flowed out of one body into another, like water does from a higher gravitational potential to a lower. But that's contradicted by the fact that you can produce heat by mechanical action alone, such as in friction. So where's that heat coming from? It's coming out of the substance, and it seems to be inexhaustible, right? You can produce a hell of a lot more heat, and the substance never seems to run out of the potential to produce more heat by this friction. So there's all kinds of different arguments back and forth as to what's producing the heat. Is there a fluid? By Planck's time, people had pretty much abandoned the idea of a caloric fluid, and we're trying to explain heat by simply the motion of atomic, what they refer to as, atomic particles or molecules. But no,
Where was that Einstein quote from?
that's from his autobiographical note. So, this is it's a very puzzling question in terms of these are some of the puzzling questions. People were part of the theory was that at the time, without going through the whole details of it, that scientists had to account for the existence of heat as simply the motion of particles. This was not new at that time. Daniel Bernoulli actually was one of the first people to come up with this idea. But remember, this is in the beginning of the 19th century, where nobody had actually done any experiments that even demonstrated the existence of what today people think of as atoms and molecules and so forth. So forget your high school chemistry association with this idea. But here's the problem here's the other point here's how Kirchhoff honed the thing down to this following problem, that when you have there is a relationship between light and heat, in that the hotter a material body is, or let's state it this way, as the heat in a material body increases, the color of the light that it emits changes towards the higher frequencies and also becomes brighter or more intense. Intensity is the scientific term. Brighter is the intuitive term. So you know this experience just from looking at a stove, right? When you first turn on the stove, it actually starts to radiate heat without changing color, which is why you have to be careful not to turn on the stove on low and walk away, or somebody's going to burn their hand. Right? But also, as it gets hotter, it starts to glow red, and the hotter it gets, the brighter the red gets. And if you were to keep heating it up, it would start to turn yellow. And if you look at the welder, you've seen going by a construction site, and you've seen these welding torches or arc welders, you see how hot they're getting. And when they get real hot, they start to glow white. And they're so bright you have to wear very heavy goggles to protect your eyes. You can see it it can hurt your eyes from looking at it from a block away. It's that bright. So there's this relationship. And
They do that with stars too, right? They have different colors the stars will be.
because of what Kirchhoff did. See, Kirchhoff did these, I'm just giving you an intuitive sense, but he designed very, very precise experiments to determine this exact relationship. And this became a major subject of investigation among a lot of people who were looking at this. And a guy named Stefan had figured out that the frequency was proportional to the fourth power of the temperature. So it goes up pretty fast, right? That the color changes proportional to the fourth power of the temperature. But
you're saying Kirchhoff developed precise experiments to show the relationship.
to show the relationship between the color and intensity of the light and the heat. And the particular experiment which universalizes, which eliminated all the extraneous factors, he called black body radiation. You've probably heard that term before and not know what it's about.
So that wasn't Planck?
Planck solved the problem. Kirchhoff designed the problem. So the black body radiation comes from, is the design of the black body radiation is the following. That what Kirchhoff showed that a body absorbs light exactly the same way it emits light. So if you have a green body, it absorbs all the colors except green, which it reflects. So it's not going to absorb any green, and if you heat that body, it's not going to emit any green, right? So if you have a white body, it reflects all colors. It's a perfect reflector. Conversely, a black body will absorb all colors of light. So, and as I said earlier, he showed that this relationship between the heat and the color and intensity of the light was independent of the material. You could use iron, copper, some alloy, anything. And the temperature and the color of the light were the same. So this is not something that is specific. You're looking now at some universal interaction between what we call matter and light and heat, which all matter reacts with light and heat the same way. So it's, you've got something universal.
So no matter what the material, at a certain temperature, it's going to give off the same color.
At the same intensity.
At the same intensity.
Yeah. It's a little more complicated than that, but that's good enough for right now. I'll get to the more complicated part in a second. Okay, so he designed this apparatus called black body. And I actually had the good fortune, they had when I was in Berlin in 2008, it was the 150th anniversary, I think, of Planck's birth. So they had an exhibit at the Technical Museum in Berlin, which was a terrible exhibit. The only thing interesting about it was the little piece at the beginning where they had stuff about his early life, and that's where I found out about the music ovens.
Huh.
But if you went to that exhibit and tried to learn anything about Planck, you would have been completely confused. But they did have one of these black body experiments. Okay, and what it looked like, it was a cylinder about that big.
Can you use a darker marker, please?
Yeah. It was just a cylinder.
Your markers absorb
Okay.
too much light.
And, of course, you could only see the outside of it, but I know what was on the inside. Okay, and around it was basically what looked like asbestos, covered in cloth. Okay, so that it was perfectly insulated. So it'd be like if you had an oven, and your home oven was so perfectly insulated that you turn on the temperature to 200 degrees, and the oven goes beep beep, and then you could turn it off and it would stay at 200 degrees for forever. Right now, you turn the oven at 200 degrees, it's pretty insulated, but you feel the heat coming out, and so it has to keep going on and on and off. On and off, on and off, on and off, right? But this was so insulated that once you got the heat in there, it would stay in there. Okay, now inside was a hollow, the cylinder was hollow, okay? And the inside of the cylinder was painted black, covered with carbon. Now, Planck showed actually that you don't even have to do that. All you have to do is have a tiny, tiny piece of carbon in there and you'll get the same effect. But to make it simpler, they coated the inside with black. And then it had wires going in there, elements, so that you could run a current into it and heat it up, heat the material up. So basically what you had was a completely enclosed oven. And so once it got to a certain temperature, it would start to radiate heat into the cavity, right? But all the heat that it radiated into the cavity, it would reabsorb. So once you got the temperature up to a certain level, it would get into a state of thermodynamic equilibrium. where it would be, the material would be radiating heat and light into the cavity and reabsorbing the heat and light that it was radiating back into the walls.
What, there's something floating in the middle, you're saying, that's the material?
No, the walls of the oven
Oh.
would glow,
Mm-hmm.
okay? And it would radiate the heat and the light into the cavity.
Oh, just into the center of the...
Yeah, this is hollow in the
Okay.
inside, okay? So imagine, so there's a little cavity in here, right? This is all insulation. And you got some wires going in here to heat it up, right? So these walls, these things are all solid, some material that conducts heat. And they would start to glow, and the area in here would get hot, right? The walls would get hot, the space in between would be the same temperature, right? And so it would stay at thermodynamic equilibrium, okay? Now, of course, if that's what you did, you couldn't do any experimental work with that because you can't see what's happening inside this cavity. And if you try and see what's happening inside that cavity, then you're going to let heat or light go out. So they had to compromise, and they poked and you saw this, they poked a teeny weeny hole, okay, in the side of that. So it was not a perfect black body. They always had to discount that a little bit was coming out. So they tried to make that hole really, really small. And then, so the light would come out, and then they would have a prism here. Right, some prism. And they would split the light out into the prism and see what colors it were. And they also had, and then they would, shine that onto a screen, and they would be able to measure the wavelengths. They had very, very precise measurements to measure the wavelengths, and also the intensity of the colors. Okay? So, what the experimental evidence showed, and it took a lot of guys to do this work over and over again. You'd have people work for years on a single wavelength and look at the light from that wavelength at different temperatures. So what it showed was that there's a famous graph. So this side is temperature, and this side is frequency of the light.
They would emit all the colors?
Yes, at any given temperature, all the colors are emitted. But there's a certain peak intensity, which is the intensity that you perceive. So when your stovetop looks black, but it's radiating heat, the peak intensity is in the infrared range. But there's also red, orange, yellow, green, blue, indigo, and violet light coming out. But it's very, very dim. So dim you can't see it.
Huh.
And when the light is, when it's glowing red, the same thing. There's infrared, there's also higher frequencies, but the red is the peak intensity.
Huh, so it just dominates.
So that's what you, yeah, that's what you, and that's why as it gets hotter and hotter, it doesn't actually turn green and yellow and blue, it gets more white, and it gets bluish white, because what happens is that more and more of the higher frequencies are added into it, and so you get more of the mixture of the lights, and it tends to look more white. So the profile is that at low temperatures, you would have a peak would be in the low range, and then the high ranges would drop off. And as the temperature got greater, the peak would shift more towards the red, and then more towards the violet, and you would get curves something like this. Okay? So you have two problems to solve. One is, why does it have a peak and then drop off? Because if the light were waves, just ordinary waves, think about, you got waves in a bathtub, which is, you got a bathtub filled with water, and you drop something, you drop a drop of water, you set up a wave thing in there, and the waves, first you get these long waves, and then they hit the sides, and then they start to come back, and the waves start to get more and more frequent, and as it starts to get to equilibrium, the waves get more and more towards the higher frequencies. So if it were just an ordinary wave, you would think that each one of these curves is the curve when everything is in equilibrium here, when the temperature's not going up or down, when the bodies are emitting, absorbing and emitting exactly, you know, they're in equilibrium. So why does it drop off? And the second thing is, why does the peak intensity change the way it's changing? Because it's not a smooth curve.
You said that it's a, there's a fourth power relationship in that?
There's a fourth power relationship to the frequency to the temperature, but that's just the peak. That's not the whole picture. It gets more complicated. It doesn't really. That's just the first approximation. That was the first approximation. But when they did more careful studies, and especially when they went and looked at the infrared, it took a long time to develop an apparatus which could measure really well the infrared, the light and heat relationship in the infrared spectrum. So this is a problem very similar, at least in the way it's set up, to Leibniz's discovery of the catenary. You have a physical process, the hanging chain, which is a least action principle, right? It's a state of equilibrium. The chain appears not to be moving, right? But its lack of motion is the result of the fact that it actually is the principle of motion. And all the mathematical curves, all the people who tried to come up with mathematical curves to express this, what the physical world was doing, failed, right? Galileo said it was a parabola. If you take a big parabola and a small catenary, you can get pretty close. So all the efforts at trying to figure out how this relationship works were like Galileo and all these curve fitters trying to come up with the catenary. And you know from studying what Leibniz and Bernoulli did that they discovered the principle of the catenary by starting with the physics. So what's the damn chain actually doing? What are the real physics here? And the physics told them that the curve is not a mathematical curve. And they had to invent the mathematics to describe what the physics said was happening. And that the thing they discovered was something of very dramatic universal significance in terms of what the catenary did. Now, here's what Planck. So this is what people were doing, and Planck was trying to figure this out. What could account for this? So he had submitted all kinds of ideas in this, and they all fit almost just like Kepler's vicarious hypothesis. Almost fit, right? But there was a small error that he was not satisfied with. And so he realized that he had to make a breakthrough. And the story that's told is that, I can't remember the name of the scientist, his colleague, who came over to visit him on a Sunday afternoon. And they were having a conversation. And Planck seemed somewhat distracted during the conversation, but they had an ordinary Sunday afternoon conversation. And the guy left. And that night, Planck wrote on a postcard what his discovery was and mailed it to the guy, who got it 3 days later. And then he eventually wrote his paper on it. And the discovery, the solution he came up with cannot be understood by a type A personality. Only a type B personality can actually imagine this consequence. And here's what it is. Planck said the only way you can explain what you're actually observing is is that, here's his assumption. His assumption was, one, that the light waves were continuous waves in the cavity. And they were oscillating without giving a physical explanation for how this could occur, but just assuming that that's the case. They were oscillating. And when they hit the walls of the material of the oven, that they resonate with harmonic oscillators in the walls of the oven. And the harmonic oscillators in the walls of the oven are also setting these waves in motion. So the waves are causing the oscillators to vibrate at the same frequency that the waves are vibrating, and the waves are causing, and the oscillators are also setting the waves in motion.
So you don't have any phase cancellation.
Right. It's all in phase. And so you have this, since you have all these different frequencies, you have among the oscillators in the you have oscillators oscillating at all the different frequencies. Okay? And the peak intensity is the oscillators that are oscillating at the peak intensity are oscillating the most energetic, with the most power. And you know this from if you imagine a cycloidal pendulum, okay? Imagine our famous cycloid track, and you got a little ball, and take away the friction, so you greased it up real well. You've got a Teflon ball and a Teflon, right? So whether you drop the ball from this height and it goes back and forth, or whether you drop it from this height and it goes back and forth, it's going to oscillate at the same frequency, right?
What does that mean, oscillate?
Go back and forth
Okay.
at the same frequency, because the cycloid is the curve of equal time, right? So whether you drop it from here, it'll roll slowly here, up like that, right? So say this is 1 second. And if you dropped it from here, you've seen this cycloid experiment, Chance?
No, I don't think I have.
All right, well, somebody's going to have to do this for you then, show you how to do it, okay?
Okay.
But you can see it approximately with a pendulum with a very long, a grandfather clock has a real long cord and a pendulum on the bottom, right? And so the pendulum swings back and forth, and even though the friction at the top makes that period get smaller and smaller and smaller, right? It doesn't, the frequency, the amount of time it takes for the bob to swing from its starting position down to 0, up to the next, and then down to 0 and up to the next, okay, is always the same, or pretty close to the same. If you had a cycloidal pendulum, that instead of going on a circular track, it went on a cycloidal track, then it would always be the same no matter how short it got. That's the property of the cycloid. So the difference is that if it drops from here, it moves kind of leisurely, right? Whereas if you drop it from up here, it'll take the same amount of time to go back and forth, but it'll go with more force. Okay? So the peak intensities were oscillating with more force than the frequencies that were, say, bigger or smaller cycloids in this analogy that were going with less force. Okay? Now, why would that occur and occur in this way? Why would you have this happening in this way? So here's the bizarre idea he had, which is that, imagine that, I'll give an analogy. Imagine that you have this, let me just add one more, just one more thing, just without going into details, but just to indicate it so that you see the irony is. This can, when we get at any given temperature, this apparatus is in thermodynamic equilibrium. So its entropy is at a maximum, according to Clausius, right? It's maximized its entropy. It can't change. It's not going to get hotter. It's not going to get colder. It's going to stay at that temperature, and these oscillators are just going to hum back and forth forever, assuming you didn't let any light out. Okay, in the perfect black bodies. So it's in thermodynamic equilibrium. The entropy is at a maximum.
So you're
Right.
a little slow catching. So you are looking at the interaction of the heat and the light inside it, right?
Yeah,
So it's the
you've got it at the. You've put some power into the middle of this thing by whatever means you do, and that has caused the sides of the oven to start glowing.
so you miss the light, and the light hits the other side, which then interacts.
Or otherwise, it absorbs
Heat.
anywhere. It doesn't necessarily go to the other side. It goes to other parts. Some of the light
Right.
stays in the middle. But it's like if you had an oven that was so perfectly insulated. You turn the temperature up to 200 degrees. You hear the beep. You turn off the oven, and it stays at 200 degrees forever. Because nothing is escaping it, right? Okay. Imagine if you had such an oven, and you turned it up to 300 degrees, and the element was glowing. You could see from the window in the oven. You turned it off, and no heat escaped. That element would still glow, right? Because the heat, it would be emitting the light into the oven, but the oven, you're not adding anything new to it, right? The reason why you see it go on and off is because the way our ovens work is we turn it up to 300 degrees, it turns the element off. Then as the temperature goes down, it turns the element back on. Because if you kept the element on, it would keep raising its temperature. So this is in thermodynamic equilibrium. So Planck says, well, according to Clausius and Boltzmann and everybody else, the entropy would be at its maximum. But in order for that to happen, then something very nonlinear must be happening in the microscopic domain. And that is this, that going back to my analogy of the cycloidal pendulum, if you have a cycloidal pendulum, right, you've got a continuous curve here, and so you can take a ball and lift it up to, say, this height, and let it go, and no friction. So it would go up to the same height here and back, and it will oscillate. It will be in equilibrium forever. Okay? Now, if you were to give it a little push, instead of just dropping it, you gave it a little push when you dropped it, then it would go up to a higher point, right? And then it would start oscillating at that level forever. And if you started here and gave it a little higher push, it would go to a higher height, right? And start oscillating back. Okay, so now in this example, within the domain of sense perception, it seems that on principle, you could make that pendulum, or that cycloidal curve, oscillate at any frequency you wanted by increasing by any small amount the amount of push that you gave the ball. You could push it, however you want to measure amounts of push. You have a continuous potential for varying the amount of push you give to the ball, right? Well, what Planck said, in this case, the only way you would get this result would be if you were limited to only certain amounts of push. And those amounts of push were proportional to a very small number, which is now called Planck's constant, which he called h. Actually, he didn't call it h, it's now called h. He called it n. And
Well, because what would make the colors discrete?
no, it's not that the colors are discrete. It's that, well, let me just finish, right? It's a little number, and it's only whole number multiples of that. So 1h, 2h, 3h, 4h, 5h. And the amount of energy in the oscillations is proportional to whole number multiples of this times the frequency. So as the frequencies get higher, it takes a whole lot more power to get those things going in oscillation. But the amounts of power you can add are only in discrete units. As I say, you got to be a type B personality to understand this. Planck was definitely type B. There's nothing in the domain of sense perception which corresponds to this idea. And it was so shocking that nobody believed it.
You say the last part again?
Okay. It's the point is that what Planck said. Well, let me try and add something to it, which might make it a little bit easier. I gave you the summary version. Now let me give you the little bit more complicated version, which will have the effect of confusing you more, but also making the potential to be more clear. Then I'll do the summary again. The point is that it's in thermodynamic equilibrium, supposedly, right? So the entropy is at its maximum. Now, what Boltzmann had said, who was the successor to Clausius in this question of entropy, was that the way if Planck later, I'll just throw this out summarily, but later we'll, maybe later, not tonight, but Planck goes through, actually gets into a whole discussion about this, which is very, very important. But what Planck shows is that the assumption of the second law of thermodynamics, that a state of maximum entropy can exist, or that you have a process which is irreversible, that in order for that process in order for something like entropy to be a characteristic of that process, the process has to be fundamentally random. That is, the state of maximum entropy has to correspond to a state of pure randomness, which is another way of saying no change. You've reached the maximum change, because once you've gotten to pure randomness, you can't get any more random, right? Right? If you just a simple thermodynamic process, if you have, a hot piece of iron and a cold glass of water, and you put the iron into the water, there's a big heat potential difference between the two objects, right? But when they get into thermodynamic equilibrium, then there's no potential. They can't change anymore. You're not going to have the iron become hotter and the water become colder. It's not like you take a hot piece of iron, stick it in the water, and the water turns to ice, and the iron gets 50 degrees warmer. Right?
Or you use the example, it's not like you pour a nice hot cup of coffee and you set it down on the table and you expect when you come back that it's not going to be any cold. Or you say like you have a cold cup of coffee and it's sitting on the table and you come back a few hours later and you expect it to be hot again or something like that.
Yeah. Or you take a sugar cube and you put it into a cup of coffee, and it dissolves into the coffee, and then you come back an hour later and you expect the cube to be floating on top of the coffee. Right? So the point is that for reasons which we'll discuss later, when you get into this type of process that appears to maximize entropy, Planck is the first guy to really get into the real arguments, the logic of this, because nobody else wanted to. But he got into the real assumptions. He said, what you're really assuming, you must assume that the process is the result of a large number of random interactions, and that entropy is at its maximum when it's reached its greatest state of randomness, because then you can't get any more random. Otherwise, if there were some type of order, then it could get more disordered, right? But if entropy can only go in one direction, the only way it can go is towards more disorder. There's a point at which no more disorder can occur, right? Which of course is a stupid idea, because nothing in the universe is physically, nothing in the universe is disordered. The whole idea of randomness is a human idea. And everybody, you know, computer scientists find this out all the time, because every time they try to make a random number generator, some nerd in some computer science department somewhere, breaks a computer by proving that the random number generator really isn't random, right?
It's ironic that they choose the randomness as the measure
Right.
for the constancy and not constant change.
Right, because it's just like, you see why the equant principle is so important here, right? Because it's just like what it meant for the world, for Kepler to say there is no equant. So what do you measure the time by? What do you measure the motion of the planet by? You measure the planet's motion by the planet's motion. You can't measure it by something else. You can only measure the motion of a planet by the motion of that planet. The area, it's not the areas, equal areas are swept out in equal times. The areas are the time. That's the measure of your motion, and that is your time. Right? So this whole idea of randomness is the same problem. Because you're in a sense introducing a new form of equant, maximum disorder. Right? Which is another way you can see, inversely, why such a universe has to be finite. A universe that is maximizing its potential for change would be finite yet unbounded, because there can't be any final resting place that it gets to. Every time it makes a change, that has to create the potential for more change. And that has to create potential for more change. So it's tending away from a state of maximum disorder towards a state of higher order. So what Planck said is, okay, if this is in maximum, in the case of this thermodynamic equilibrium, this has to be in the state that is the most probable state for it to exist. That's why it's doing what it's doing. And if that's the most, and the only conditions that would make this the most probable were if the oscillations of the oscillators could only be at certain levels of power, in discrete levels of power. So the mechanical analogy I have, which is the best I've come up with yet, I keep refining this because I think I'm getting better at it as I try it. But if you have this cycloidal pendulum, you see that the one way to think about it is that the height that the ball is rolled from or rolls to is greater. The greater the height, the greater the power that it oscillates with. Right? The frequency is the same, but the power is greater. Another term for the height would be amplitude. Just like if you have a sound wave, you can have a C at 256, which will, at a low volume or a high volume, the frequency is the same, but the power of the sound is greater. So in this case, with our pendulum, the greater the height, the greater the power of its motion. Okay? Now, in your mind, you can think, well, since I have a continuous curve, and I have a continuous continuous possibility for energy for power states of this thing oscillating back and forth at the same frequency. A ball oscillating at this frequency, whatever it is, one oscillation per second. Okay, say it takes 1 second to go from here to there and back to here again. Okay, so I can oscillate at 1 oscillation per second at a infinite number of different amplitudes, or with an infinite amount of different levels of energy, right? And I could get that either by raising the ball up to different heights and dropping it, or taking it a small height and giving it a little push. Okay, now imagine this. Let's try another little thought experiment. Suppose you lift it up to say 2 inches off the table, and you let it drop, and it goes to 2 inches off the table here, goes down to 0, up to 2, and it oscillates back and forth between 2-inch heights every second. Okay? Now imagine you lift the ball up to 2¼ inches, and you let it go, and it still only goes up to 2 inches and starts oscillating in the 2 inch to 2 range. And you pick it up to 2½ inches and you drop it, and it still only oscillates between the 2-inch range. And you pick it up to 2 3/4, and it's still only, and you drop it, and it still only goes at 2 inches. And not only does it only go for 2 inches, but it does something really eerie, which is, here's your cycloid. So you pick, well, here's our 2-inch range. So I pick it up to here, and I let it go, which is say 2¼ inches off the table. And I let it go, and it doesn't rotate, it doesn't fall from here to here. It jumps from here to there, and then starts oscillating back and forth, right? And then I pick it up right here, and it jumps to here and starts oscillating back and forth. And then I pick it up to here, and it jumps again down to there. Does not do anything in here. It goes back and forth.
But then when you get it to 3,
Then when I get it to 3, then it starts rotating back and forth at 3. Okay?
Doesn't jump up at all.
Something like that, he says something like that must be going on. And unless you assume that the organization of this interaction between light and heat with material objects is occurring in this quantized way, you would not get the experimental results that we've so carefully measured.
But maybe
Go ahead.
Do you also have gaps like that, not just in the amplitude, but also in frequency?
No, the frequencies, you can get any frequency, but the intensity,
So then that means you have all frequencies
Yeah.
oscillating, but the amplitude, there's these
right.
gaps.
Yeah, which is why it dies off as you get to the higher frequencies, because the higher frequencies take more energy.
Because the gaps are bigger.
No, because it's in the total power is proportional to whole number multiples of that little number times the frequency. So if the frequency is greater, then the total, then the frequency number gets bigger. So one unit of this times a low frequency is a smaller amount of power than 1 unit times a higher frequency, for a higher frequency. Now, yeah,
So I'm not clear, how did Planck conclude that to address that, these different peaks, that you needed this quantized effect?
because that's why, two things. First of all, that's how come, if you have it this way, then at any given temperature, equilibrium would occur in such a way that you would get a peak in the lower frequency range, and it would die off as you get to the higher frequencies, because those frequencies would not have a lot of intensity to them. And the second is that as you increase the temperature, the peak shifts towards the higher frequencies, but the peak shifts slower and slower towards the higher frequencies. It takes more and more temperature to get up to a higher frequency. And this,
Those are both continuous, right?
yeah, and this This corresponds also to another phenomena, similar phenomena, that Einstein later solved with respect to specific heats. The specific heat with respect to a particular substance is the amount of heat it takes to raise the temperature of that substance 1 degree, right? And that is not the same amount of heat for at every temperature. There was a paradox in the phenomena of specific heat that it takes, as the temperatures get greater, it actually starts to take more heat to raise the temperature of that particular substance by 1 degree. So there were these nonlinearities, and that's the kind of thing. So the rate at which it's changing can only be explained if you say that to get equilibrium in the macroscopic domain, you have to have this quantized effect in the microscopic domain.
I don't understand how that leads to this the necessity for the quantized effect.
Because if you have the quantized effect, then in order to get a shift to the higher frequencies, you need to put a huge, the higher the frequency, the more power it takes to get a shift of the peak just a little bit to the right. And if you try and do it with a continuous curve, it doesn't function. You can only do it with a discontinuous curve. And Planck then made the calculation, and every experimental result up to this day, the more precise they got, the more it conformed to what Planck said.
So those curves are incorrect?
No,
Or are you just talking about?
those curves
if you
are
go in
correct.
between, if you go from curve to curve to curve?
No, within any given curve, that's at a particular temperature,
Yeah,
okay?
yeah.
And the curves at that temperature then is when it's in equilibrium.
Mhm.
But in order for it to get that profile, in order for it to have a peak and stay at that peak, and then not continue to get to the higher frequencies, like if it were just waves like you have in your bathtub in the water, as they get towards equilibrium, they get more and more towards the higher frequencies.
Right, right.
But imagine if
Right,
you,
so you'd expect it to be like that.
That's right.
That kind of a curve.
So it would
Yeah.
be, the curve would go up,
that's how
up,
you
up,
would
up,
expect it,
up.
right, if it was
Yeah.
water, but it doesn't do that. It goes
down.
It goes down.
Yeah, yeah.
So why does it go down? Because at that temperature, these little quantized oscillations produce more action in the lower frequencies, and there's not enough of them to get the higher frequencies going. It's a crude way of putting it. Huh?
They get tired.
It takes so many of them to get the higher frequencies going, there aren't enough of them. As you increase the energy, as you increase the temperature, there's more of them.
So what
That's
does that
weird,
mean
yeah,
then?
because that's strange.
It's strange, and it gets even stranger.
How
Because
do you
here,
keep it equilibrium then, if that,
that's the point.
you know?
That's the paradox, right? Now here's where it gets stranger, okay? As far as Planck was concerned, he didn't know what was going on, but he knew whatever was going on in the, he only said was going on in the matter, in the walls of the oven. Okay?
Cool. Could this correspond in any way to the way Larry Hack just wrote the relativistic considerations of the moon model? And then it's got this concept of the oscillating.
Yeah. This is all of modern atomic science is based, has to take this into account. It gets more, there's a whole lot of steps between here and there.
So he's got this concept of the oscillating particles in the nucleus.
Yeah.
And,
Yeah. But Planck was not describing, this was before the experimental evidence of the atomic nucleus and all that had actually been finalized. So Planck was not making a hypothesis as to what the physical characteristic was. He was just saying that has to be some kind of character. But then he said something, then it gets even more interesting. Because he said, okay, this quantized effect is happening in the walls of the oven. but the light that's inside the oven are these continuous waves. Okay? Now Einstein came along 5 years later, and this is actually his first paper in 1905. He wrote 5 papers in 1905. And the first one was called On a Heuristic Concept of the Theory of Light, or something like that. I can't remember the exact name of the paper off the top of my head. But he used the word heuristic in the title. And he said, if we actually assume, he proved, actually, that we could actually get the same result that Planck gets by starting not with the walls, the oscillators in the walls, but that the radiation in the cavity, the light and the heat inside the cavity, was not continuous waves, but was oscillating, small oscillating quanta of light. And that these small oscillating quanta, that the quantized effect was not just in the material, but was also in the light. Now, he says in his paper, it uses the word heuristic, right? Which means that it's an idea which will lead to, it's an idea you're proposing in order to lead to a more, you're not saying that this is the real solution, but you're proposing it in order to lead to the solution. Okay? So he said the light itself is quantized. And he says in the beginning of his paper, he says, the wave theory of light is so well established by experiment that it can never be overthrown. Nevertheless, when I look at this phenomenon of black body radiation, it leads me to hypothesize that there's a quantized effect of light in light itself. And then he says that if you assume, if this were true, this would help explain something which was just beginning to be investigated, called the photoelectric effect. Now, the photoelectric effect is also
But it was Planck's discovery that led Einstein to hypothesize this.
not totally. Einstein went one step further, because Einstein was also, this was the same year he did relativity. So he was also trying to deal with this question of a universe that must be everywhere changing. Which is why he rejected the... Remember, Einstein talks about how when he was 14, he had this idea about what would it look like if you were moving at the speed of light? What would a beam of light look like if you were moving at the speed of light? So I think you have to be really careful with Einstein, like all creative people, of trying to come up with a logical explanation, step by step, of how they made these different discoveries. As he himself says, there was a lot of wondering going on, right? And a lot of this wondering led to particular discoveries, but he never stopped wondering, which is why he writes his paper in 1905, okay? For the next 50 years, there becomes a huge battle in all of science where the people like Niels Bohr and Born and some of these other people who were directly working for the British Empire took this concept that Einstein and Planck had of quantized effects and turned it into this dogma called the Copenhagen interpretation of quantum mechanics, which people walk around today with thinking they know something about because they talk about photons and all this other stuff. But 50 years later, in 1955, a few months before he was going to die, he knew he was going to die too. He wrote a letter to his friend from 1905 who had gotten him the job at the patent office in Zurich, Michel Bessel. And he says, to this day, I still don't know what light quanta are. So Einstein never stopped wondering about these things. He was driving science forward and saying, you know, the the physics, the experimental evidence, and what I know the universe must be like requires me to go here, but I can't, each question poses more questions, right? So in 1905, I think he was just full of a lot of these questions, and it was leading him to overthrow all these things, which is why I said at the beginning that Einstein should be most revered for the thing he's the most criticized for. Whereas everybody else wanted to make a dogma out of this, and they said, oh, Einstein, you're just refusing to accept the consequences of your own discovery. And Einstein said, no, I'm refusing to accept what you say the consequences of my own discovery are. I still got questions. You're trying to put periods where there should be question marks. So let me just give you a short thing on the photo, just what it is, and then we'll have to do this again to follow this up. But the photoelectric effect is simply this. If you take light and shine it at a piece of metal, you can get an electric current off of it. And the strange thing is that if you increase the intensity of the light, say you have your light source here, if you move your light source closer, the intensity of the light that hits the metal will be greater. If you increase the intensity, the power with which this current is coming off the metal doesn't change.
For frequency?
If you keep the frequency the same but increase the intensity, the power doesn't change. But if you increase the frequency, then the power changes of the current.
At the same intensity?
The power doesn't change in it with a variation in intensity. It only changes with a variation in frequency.
Right. But I'm saying that, say if you have a frequency, a particular frequency hitting the metal at a particular amplitude, if you simply change the frequency without changing the amplitude,
You still increase the power.
you still increase the power.
Right. Right? Now, that contradicts the idea of a wave, because if you're on the beach, and you got a wave coming at you, if you're standing close to where the wave is, you're going to feel more, you're going to feel the force of the wave more, right? But if you go back on the beach, the wave is, right? So if you would think that if you increase the intensity, you would get a greater power. But you don't. So Einstein says, well, of course, if light were actually this light quanta, and the power of the light quanta was proportional to the frequency and Planck's constant, then the photoelectric effect would behave like it does. Now, nobody had really done the experiments to see if the photoelectric effect behaved the way Einstein said it did, until Einstein did this. Then they did all these experiments to prove it. And that's what he eventually won the Nobel Prize for. But ironically, they didn't give him the Nobel Prize for what he actually discovered. They made it up. They said they gave him the Nobel Prize for discovering the photoelectric effect. He didn't discover the photoelectric effect. It's like the very end of his paper. The main thing in his paper is an extension of what Planck is saying, that there's this contradiction between a state of equilibrium and to achieve a state of maximum entropy, you would have to have something which is very nonlinear in the microscopic domain. And to him, this was a big question mark. And then the whole 20th century is, the history of the 20th century is the fight between this view that Einstein has and these others who are trying to recreate the Clausius, Lord Kelvin view of the second law of thermodynamics.
Doesn't Bernowski talk about that? This question of equilibrium and the kind of changes that go into producing things that look like equilibrium?
Yeah. Yeah. Well, the point is, what is the state of equilibrium? You know, Planck gave a series of lectures at Columbia University in 1908, where he describes a lot of these things. He also wrote an essay, which is quite instructive in this, called "On Dynamical and Statistical Laws." And we should probably, do another discussion where we can get into the meat of these kinds of things. But what Planck is saying, what he basically boils this down to, is that what you're really dealing with here, what he says, is a question of processes that are reversible versus irreversible processes. And when you're talking about things like a pendulum swinging, or a planetary orbit, that these are reversible processes, because a pendulum can swing from its high point to its low point, and then it swings back to its high point again, and then back to its low point. So it reverses its steps, right? But you have other processes like the sugar, or he uses the example of the radioactive decay. You've got a lump of radium, and you've got one atom of uranium sitting there, stable for 1 billion years, and then all of a sudden just blows up. And the atom of radium just next to it stays completely the same. And that radium that just blew up, the radium is not going to go back to its previous state, right? The radioactive decay goes in only one direction, right? So he says you do have processes in the physical universe which go in only one direction. So it's not irrational to conceive of a quantity which measures the rate at which things, or the stage at which something is towards that state of irreversibility, right? But here's the thing that Planck, here's where he knows he's got a problem, which is that he says does not characterize the way human beings function, because human progress, like we were discussing creative ideas, these are also irreversible processes, and they don't go towards a state of equilibrium. Each discovery leads to an increase in potential for more discoveries. And now this essay is kind of, there's an interesting little story about this, which is that it was actually adapted from a lecture that he gave. And there's an English translation of it that's put in this book called The Survey of Physics, which is a little paperback book you get for $1. But in the English translation, it doesn't say when it was given, and they don't translate the first 3 paragraphs. When you get the German translation of it, you find that it was given in August 1914. Remember what was going on in the world in August 1914? You're just about to have the outbreak of World War I. And he gives this lecture at the Kaiser Wilhelm Institute in Berlin. And he starts by saying, conscientiousness and a commitment to truth is essential for all science. And it's essential for maintaining organization, social organization, and so forth. And he says, but the problem is that nobody knows what might happen tomorrow. Our whole nation might not exist tomorrow because of things individual people might do. And then he says, then he goes through this whole discussion about these types of irreversible processes, and he draws the conclusion that if you've got processes that are irreversible, it assumes that they must be fundamentally random in the small. They must be, the only type of physical irreversible process is one which is going from a state of higher order to lower order, right? And then in the last paragraph he says, but, he says, that's just the non-living world. He says man is not governed by those principles. Man is governed by moral law. And moral law goes the other way. So he understood this, right, from his work in science, from his work in music, philology, and because he was a serious thinker. But he was not as, he came from a different, background than Einstein. So he was less able to really rebel against it, whereas Einstein was sort of a rebellious person from his very early age. And it's that rebelliousness, which is why the ironic thing is that Einstein, who left Germany when he was 14 and renounced his German citizenship, went to Berlin because Planck recruited him there. And Planck arranged for Einstein to get this appointment in Berlin, where he wouldn't have to, he would get paid without having to work. Just to think. He got appointed to the Prussian Academy of Sciences and didn't have to teach any courses or do anything. He just had to do it. So Planck respected Einstein's thinking so much that he brought Einstein to Berlin. And Einstein respected Planck so much that he stayed in Berlin until the Nazis took over. And he didn't almost go back, but he was in the United States when Hitler took power. And then shortly after Hitler took power, they raided his house, Einstein's house. At that point, he realized he probably couldn't go back. But he was always worried about what would happen to him. I mean, there was that much of a, even though all these terrible things were happening to him in Germany, all during the 20s and early 30s. He got a big difference in his outlook, though, when he came to the United States. In that year, 33, he went back to Europe, and he had accepted this appointment in Princeton to be but he wasn't going to live in Princeton. He wasn't sure what he was going to do. He actually, the British were trying to get him to come to Cambridge. And he spent the summer in Belgium, in Holland, actually, I think. And he then came back to the United States, and he decided he would stay in Princeton. But since he had come in as a tourist, he couldn't stay. So he left on a boat to Bermuda and came back and made an official application to be an immigrant. And they offered to pass a special bill in Congress to make him a citizen without having to go through the process. He declined it. And he went through the normal citizenship process. And he became his outlook on things changed a whole lot once he got to the United States. It was he never left the U.S. again. Never went to Europe again. But that's a whole other story, what happened. Lynn talks about it a lot, the Solvay conferences and what happened in the 20s and so forth. And when you look at it, that whole brutal assault on Einstein and Planck was done in order to defend this, not the second law of thermodynamics per se, but to defend what the second law of thermodynamics stands for. The idea that the universe is fundamentally anti-creative, whereas Planck and Einstein understood that the universe was fundamentally creative. They didn't, the one criticism you can have of them is that they didn't understand what Vernadsky later developed, but they weren't looking at that evidence. They were not, Einstein dabbled in it a little bit here and there, but they didn't get into it. He didn't look at that experimental evidence. But he really, and that's the sort of the puzzling thing. Vernadsky knew a lot about Einstein, but Einstein doesn't seem to know much about Vernadsky. Which is probably one of the big deficits of science in the 20th century. But it's okay, now they've been introduced by Lynn, so they know each other and they're good friends and they're working on these ideas in the basement there, Vernadsky and Einstein, and now they can do that. do that. You're not, these things aren't permanent.
Where was Einstein in 1905? Is that in Berlin?
In Zurich. His
You
father,
said he left when he was 14.
what happened was he was born in Bavaria, near Munich. And his father and uncle had a company which made electrical machines, transformers and stuff. And they went bankrupt because they lost the contract. They bid on the contract to produce the electric lights, electrify Munich. And they lost out to a company which was the same size as theirs at the time, called Siemens.
Yeah.
So they went broke. And so they moved to Italy to try and start a company there. Well, Einstein stayed in Germany for another year to go to school, and he got fed up with it and then dropped out of school and went to Italy, and his parents had a friend, I think, in Zurich or something, and they got him to go to Zurich, and he went there, and he finished his high school and then tried to get into, he begged his way into the technical university. And after he got through the technical university, he couldn't even get a job as a high school teacher. So his friend, his college buddy, Michel Besso, got him a job at the patent office. So that's what he was doing. And he was there when he was working. He had a full-time job. He worked, whatever they worked at that day, 8 to 6 or something in the patent office, reading patent applications for machines and then at night he'd go write these papers. And he wrote 5 of them in 1 year. And one of them was relativity, one of them was the last thing on E = mc squared. The first one was the thing on light quanta. And the other 2 were about Brownian motion and the size of atoms. He used the physics of the dilution of sugar to determine the actual size of a sugar molecule. It was the first time anybody had come up with a way to calculate the size of a sugar molecule. And he was the first one to show that the Brownian motion was due to the motion of molecules of a fluid. And that's what he did that 1 year. And then he became quite famous for that. And he was offered a job in Prague. So he went to teach in Prague for a few years. Not even less than that, a year or something. And then he got offered this job at Planck.
With the so he kind of turned around with Planck's idea of the harmonic oscillators in the wall of the.
He said not only were
So they both were quantized.
Yeah, he said this quantized effect is a universal phenomenon.
But so it didn't say that the quantized effect is no longer in the walls. It's only
That
in light.
both so-called matter and energy were both quantized.
Mm.
But then remember that he didn't make a distinction between matter and energy.
Right. Yeah.
Right? See, the part of the problem you have understanding this is you try to understand it thinking that Planck, especially Einstein, Planck maybe less so, but that Einstein had the assumptions of the separation between matter and energy and then came to the realization that there was no separation. It's like trying to understand Kepler by thinking he actually did believe in Ptolemy, Copernicus, and Tycho Brahe first. If you take the new astronomy and you say, well, first Kepler believed this, what he says in chapter 1, then what he says in section 2, and that's the way he wrote the book, but that's not how he made the discovery.
Right.
In the Mysterium, he already has the whole idea.
Right.
of the harmonic concept of gravity as an idea. And the discovery he made on the orbit of Mars, he made by what Einstein calls wondering. And then he presents it in this way.
Right.
As a pedagogical way to communicate the ideas. Einstein said once it gets into words, then you can communicate it. So you can't, you know, the way you get from the words to the idea is not, it's in a sense, it's an irreversible process. You have to go to the mindset, you have to get the words, and then you've got to stop and think and do the wondering yourself. And from the wondering, then you can find out what's going on in Einstein's mind. And even in his autobiographical notes, which he wrote in 1949, he said, here's how I came to these discoveries. At least, here's how today I consider I came to those discoveries, which is not the way I was thinking at the time. But you know that from your own experience, right? You look back on the discovery you made previously, and you say, okay, now here's how I probably came up with that idea. But that isn't the way you actually came up with the idea at the time. Because you're always changing.
Right. Well, and then later, you can have even better ideas sometimes
Sure.
about what might have actually.
Right.
So when you're in the moment, you might not be consciously aware of everything's affecting you, everything you're thinking
Yeah.
about.
It's not a logical process. Why Lynn keeps talking about, you know, you've got to not, you've got to break with mathematics altogether. There's a difference between mathematics and insight, this quality of insight. That's what you want to make yourself conscious of, is the insight, this power of insight. And when you're studying a great thinker like Einstein or Planck, what you're trying to do, what you have to do is try and recreate that quality of insight in yourself, which you're not going to get from the mathematics. The mathematics is something that they use to write it down for the particular audience they wrote it down for. And that audience was a mixed audience. Some of it included creative thinkers who didn't need the mathematics, and some of it, were jerks who they put the mathematics in to convince the jerks, right? And some of it was a form of shorthand by which creative people will communicate with each other.
Shauna, when she was doing her Einstein series, she made the point that there were times, because Einstein was such an honest person, in a sense, he just kind of thought everybody was, goodwill, so to speak, that certain people will say, look, Einstein, put it in a formula. And once he tried to muster the capabilities to put it in a formula and he would come across technical difficulties, all the paradoxes that were clear to him physically suddenly became confusing. And he just wasted all this time trying to produce formulas because people were pressuring him to do so.
Exactly. And he cursed it. He kept saying, this mathematics, I don't have the mathematics. The mathematics is wrong. The mathematics is wrong. And I think part of his frustration came from the fact that he was so isolated in terms of his fight that you see in the Solvay conferences. But even before that, the other side took over, dominated, right? So if you were a young scientist, if you were in your 20s and you wanted to make a career in science, by the time the late 20s or early 30s rolled around, you were going to go with the Copenhagen guys. And he had a hell of a time. I mean, he liked to work alone. He did a lot of his work alone. But he also liked to have young collaborators around, one or two bright young collaborators who he could work with. It would help him, because as you get older, you know, the details get harder to follow. You know, you get better at the concepts, but harder at the details. So he always wanted young people to challenge him. And when he was at Princeton, he would always have a group of young people around him, right? And they were always torn between, you know, well, it's good on your resume to have been an assistant to Albert Einstein, right? But it's bad on your resume to say you actually held his views. Right? So, and the succeeding generations were less moral than he was. You know, Lindsay even talked about that. You know, he talked about the moral superiority of the World War II generation over the boomers. But he's had pretty harsh criticism for the morality of the World War II generation. And his parents' generation, even. You know, by the turn of the century, the generations that were born in the Einstein was born, what, in 1870? 1875. It's about the same age as my grandfather. But Einstein was, but, you know, so most of his generation was more moral than the World War II generation, but especially in Europe. In Europe, it was, that's why I think Einstein had a lot of confusion in his mind until he got to the United States about politics. He had the right intentions, but he got misled. When he got to the United States, he got more clear. But you can see it. Like, for example, it is the same quality that you just described that Shauna talked about. If you look at, you know, Einstein, he came from a Jewish family that was not religious, an assimilationist family of Jews. He spent 1 year when he was 13 or something, or 12, where he became Orthodox for 1 year, and then he rejected that. And so he was not a very religious person, and he tried to stay away from the Zionist movement. But because he was a famous Jew, and because he was being attacked for being a Jew, he used to joke. He said, you know, the Germans call me a Swiss Jew, and the British call me a German scientist.
That's funny.
So, so he eventually caved in and agreed to do a whole lot of money raising for the Zionist movement.
But he didn't let them nominate him to be president.
Well, that was much later. But this was even in the 20s, okay? But he helped found the Hebrew University in Jerusalem, because he said, you know, if the Jews are going to be there, they got to have a university. They offered him before being president of Israel. They offered him the head of the Hebrew University, and he didn't take it. But when the state of Israel was founded, actually before, when they started to treat the Arabs, when he saw the ways they were treating the Arabs, he wrote letters. Remember, Norton Mesvinsky mentions this, about how Albert Einstein wrote letters criticizing the Zionists for the way they were treating Arabs, and saying, you know, the Jews will be judged by how we treat the Arabs. So it's a similar type of thing. He had Lynn said, you know, any mistake he made would be an honest mistake, because he had a stubborn commitment to the truth. And that's why I think they didn't resolve this question the way it should have been resolved, because, you know, they didn't look at what Vernadsky was looking at. And Vernadsky didn't see what Lynn had seen. You know, Vernadsky has a lot of very powerful things about life and non-life and the biosphere and the noosphere and so forth. But Vernadsky's concepts are not adequate, they don't get to where what Lynn gets, because Vernadsky doesn't get this question the way Lynn has it in terms of the social aspect of ideas. It's implicit, but he doesn't have it like Lynn does in terms of the question of the self-conscious understanding of the power of music and art for the development of scientific ideas. It is not the individual discovery. The discovery is in the individual mind, but it's not the individual mind which makes a discovery. It's the individual mind participating in the development of all human knowledge. That's where the discovery comes from. And it's the effect of the individual on all mankind, past, present, and future, which is how ideas actually affect the organization of the universe. And that's why artistic discoveries are primary, because it's artistic discoveries, it's only through artistic discoveries that you get the insight into how the mind works with relationship to other minds. Which is why the choral work, for example, in our movement is so important, because it's in the choral work that you're dealing with the interaction of creative minds working with other creative minds to produce a creative idea. This is, it's the other thing that, you hear the things that, like, it's interesting, the way Planck and Wertheimer and Planck and Köhler, and Einstein and Köhler and these guys talk to each other and speculate, thought about this question of that the solutions to physics have come in discovering how the mind works, and solutions to how the mind works will come from discovering the physics, right? But they all did it as individuals, as psychologists or physicists. Lynn not only is someone who is all these things, who got himself into the middle of these kinds of problems, but he also has created a social environment by which you can apply the efforts of human minds, a greater number, increasing number of human minds in this kind of dialogue. It's just how you're going to get these solutions to come out. So the discovery of an individual comes out of that process of discovery. It doesn't come out of the process of somebody sitting off in a corner making a discovery. If you look at Planck and Einstein, even though they were solitary figures, they come out of a history. Planck was steeped in this German culture of classical music and philology, and Einstein as well, even though he reacted, understandably, to some of the reactionary right-wing stuff that he confronted in Germany in his youth, which he attributed to nationalism. So he had this reaction against nation states. But he never knew what a nation state was till he came to the United States. Then he learned what a nation state could actually be, and he developed a different view. Right? So, but he was steeped in that German culture too. He rejected the bad part that was happening to Germany. But his ability to develop these ideas was his love of Mozart, of Bach, his mother's involvement with Schiller. His mother used to read Schiller to him, So these were things that were, and some of these things you get through your culture even though you don't get them directly. You get them because, you just think, for example, of the effect of Shakespeare on English language culture and how many of Shakespeare's ideas permeate our culture, even if that affect people who've never even read Shakespeare. It's weaker, obviously, if they've never read. So that's really the important thing to reflect on. That's why I say now, Einstein and Vernadsky, they're all working together now. Making progress on it, so.
Cool.
I'll get it to you when I get it more along. And I get more ideas the more I see what you guys are doing too.
Are you reading Wertheimer and these guys?
Oh, yeah, I've read all that.
So you look at Curler?
Oh, yeah.
You know the relationship between all of these?
Well, the stuff, I knew a lot about these guys beforehand, but I didn't know this Planck-Curler connection until Sky came up with it. So that was quite interesting to me. So, having been cued into it by Sky, I went and got myself up to speed on it.
Have you read the Task of Gestalt Psychology?
Long time ago.
In there, he's explicit. He says, Sky bought it for me, but he says that him and Planck, he
Yeah,
says he got
that's
his.
where he got that thing, Sky got the quote from, right?
Oh, is it from him?
I think so.
Oh,
I don't remember.
I don't think so.
It was from something from Curler.
Yeah, that's a really short book. It's 3 of the speeches.
Okay.
It's a really short book, but in there, he references Planck as someone who taught him and helped him develop his concept of the Gestalt.
Mm-hmm. Yeah, so see, there was a lot of discussions going on, only little pieces of which are actually reported, and they're not the whole discussion. So you have to infer what the real discussion is. I mean, Wertheimer and Einstein were very close. There's the famous story about in, what was it, 1918, after the Treaty of Versailles, right? The king abdicated, and they established the Weimar Republic. And for a while, the Social Democrats took power, and a bunch of students, anarchists, took over the University of Berlin, and they held a bunch of professors and the head of the university as hostages, and refused to let them go. And Einstein, Wertheimer, and Max Born got on a bus and went down to the university and met with the students and negotiated the release of these guys.
That's, wow.
Huh.
That's why the Born-Einstein correspondence are kind of interesting, because they were really close friends, and Born was an early supporter of relativity. And then he went into his Copenhagen interpretation, so they were friends, but they were rivals on this question. The thing is that, I mean, on the question of the way the mind works, that's why I keep coming back to Lynn, because nobody really has it as good as Lynn does. You know, so the more you look at, and you know, the more you actually get into what Lynn is saying about this, how this principle of creativity works. See, at least in my thinking, it's interesting, the Gestalt psychology is interesting. But, and Lynn refers to it, it interested him, he refers to that in Beyond Psychoanalysis. But the thing that Lynn does from Beyond Psychoanalysis, and even in DE, he outlines a positive conception of what creativity is, right? Which nobody else has really done, except the artists. You know, the only, you know, you've got to look at Schiller. You know, Schiller's aesthetical writings start to get into this, but Lynn gets somewhere that Schiller doesn't. But, you know, in terms of the way in which creativity actually works, I think that all the so-called psychologists, even the better ones, are trying to figure out how that works, but they don't get what Lynn gets. Lynn really sort of looked somewhere where no one else looked in terms of this question of creativity. You know, the way he defines it is, he says you can, how do you get a positive conception of what a healthy mind is? what's an actual creative mind?
Right. Mhm. Mhm.
Today, he focuses a lot of that on this question of immortality, right? That although he had that in Beyond Psychoanalysis, he talked about the Abner Dean cartoon in Beyond Psychoanalysis. That's one of the things that recruited me.
Oh, yeah?
Yeah, absolutely,
Oh, wow.
that description of that Abner Dean cartoon.
Hmm.
Gee whiz, what was that all about?
The guy waking up at his funeral saying, "Gee whiz, what's that all about?" So Lynn was always talking about this question of immortality, and that's where when you confront that, that's when you discover what is a creative mind. What is it that you leave behind? And it's not like this discovery. What did Einstein leave us? The theory of relativity? The theory of quantized light? No. He left us the legacy of a creative thinker. So what do you leave behind? You leave behind, in a certain sense, that's a quantized wave effect too. Because it's sort of like your thoughts continuously emanate, but they originate in a very definite place. Riemann refers to that in the Geistes Mass, and he says, thinking is not material, but because it's always associated with a real human being, it occurs in a definite place in space and time. So, yeah, there's a lot more to talk about. If we get another chance, we can go into more Planck and Einstein.
Do you think there's anything connection between the moon model and this quantized harmonic oscillator
absolutely.
conception?
Yeah, I think that's what Larry's getting at. That's what he's trying to get at. That's what Moon was trying to get at.
So I'd read is just that recent article he put out. I haven't looked at what Moon actually wrote.
Well, you have the old Fusion magazines where Larry wrote about that, and then there's the 21st Centuries where he wrote about that.
Yeah, there's that one 21st century has a number of articles, I think.
I mean, there's a lot of work to do on that, but that's the direction we have to go in terms of understanding this stuff. I mean, the Copenhagen, we didn't get into it tonight, we can later, but the Copenhagen interpretation, what that does is it tries to interpret these quantized effects as being undeterminable. And what Moon was trying to get at is some type of principle that would determine these things. So, to solve that kind of problem, you really have to get into what the actual experimental evidence is. You've got to purge from your mind all these dogmatic ideas about atomic science.
Right.
Stop thinking about what you think an atom is, and an electron, and a proton, and a neutron.
Right.
Go back and look at what is the actual experiment? What is an electron? You've never seen one anyway, right?
Well,
It's a track in a cloud chamber, right?
What?
It's a phenomenon. It's like this quantum, like Einstein said. What's like quanta?
Yes, what you presented there is what they just identify as a proton, right?
No.
No? The quantized light?
No, the quantized light is what Einstein later he wrote a paper, I think, in late, like 27 or 28, in which he made this hypothesis that it'd be too long to go into it, but you back up, okay? What you're talking about with protons and electrons and all this other stuff comes out of a whole nother area of experimental work, which of spectroscopy, which is looking at the way light interacts with these material substances under certain conditions. Not how they absorb or emit light, but how they refract it. And then you look at how they absorb, what gets, from the refraction, you get a different picture of the absorption. And it's from the spectroscopy that's how you get to the proton. So you get to the first idea was Mendeleev. And he looked at the relationship of chemical properties to what was called atomic weight. What's atomic weight? It's the interaction of matter with the gravitational potential. That's all weight is. It's not an absolute measure. It's how different materials interact with gravity. Right?
Mm-hmm.
So Mendeleev develops a concept of the relationship of the periodic table based on the relationship between chemical interactions and the interaction of elements with a gravitational potential. Well, with spectroscopy, you look at the interaction of the chemical elements with an electromagnetic potential. You find that in the Mendeleev chart there are some anomalies where certain elements which are supposed to be in the columns are reversed. And so they're in the column for the wrong chemical property. But when you order them according to the spectrographic results, you resolve that anomaly. And that's what led to the discovery of the proton, was that number, that ordinal number with respect to spectroscopy. And that's what they later call atomic number. Then it became discovered that the atomic number had something to do with the amount of positive charge in what they consider to be the nucleus. But to really understand how atomic physics works, you got to go back and just learn what are all these experiments, and what do the experiments show. And a lot of the conclusions that are sort of passed down today as sort of like religious doctrines are not necessarily not the only conclusions that can be drawn from these experiments. That's the good thing about what Larry has done, is he's gone back and looked at all this experimental evidence. It's a huge body of work, right? You've got to go back through a whole century of physics experiments. But that's what you have to do, so that these ideas like proton, neutron, electron, and all those things are not just, things that your high school chemistry teacher put on the board. I always freaked out a group of, it's too bad Eric left. Actually, he was there. But I gave a talk in Mexico to a group of secondary school teachers. And this is back when we were doing this stuff on fundamental theorem of algebra and so forth. And they were asking me about education. My main purpose of the discussion was to talk about how you have to educate people by getting them to recreate their discoveries and don't teach dogma and stuff like that. Mm-hmm. And so one teacher asked me a question, and I don't know what possessed me at the time, but I said, look, you have to go back and review the experimental evidence so that people can make the discoveries for themselves. I said, take the periodic table of Mendeleev. I said, every teacher, chemistry teacher has this in their class, and they teach the periodic table of the elements as if they know what they're talking about. And they don't have any idea what they're talking about. What do we really mean by proton neutron, like, and the teacher looked totally shocked. I found out later it was a chemistry teacher asking the question. But she came up to me afterwards and said, "Yeah, you're right." She says, we don't know what we're talking about. We just don't teach us stuff. And we really like to teach people real science. All right, you guys wore me out.
Thank you, Bruce.
Yes, thank you.
My pleasure. I like every time I get a chance to talk about this stuff, it gets a little bit more advanced. I advance the process. Thank you for the opportunity.
I still don't get why this necessitates the quantized effect.
Takes a while to get,
Is it, there's something more intricate than you went through, you're saying, that there's,
yeah, you
in
have,
order to solve this.
yeah.
It's just not totally absolutely clear to me, it just seems like a little bit of a leap, but I assume there's a lot.
Well, it is a leap, ultimately. It's like, why does the catenary, the leap from trying to curve fit a catenary to actually trying to figure out what the physics are.
Uh-huh.
You can't do that unless you have the calculus, right? I mean, look at how it works in the catenary.
Uh-huh.
In the catenary problem, Bernoulli does the physics experiment, right? And writes down that differential equation.
Mm-hmm.
It says, how do you solve this differential equation? He has no solution for it, right? How did Leibniz go from that differential equation to the solution he got? When you look at Leibniz says, I can't tell you how I came up with this discovery, but Bernoulli knows what it's about. Then you go back to the Bernoulli and he shows that the Leibniz discovery is equivalent to his. But it is still a leap that why that solution to that differential equation is the arithmetic mean of two exponential curves.
Not that familiar with that.
All right, so that's a bad example. I thought that was a simple example. It's not the same solution, right? But it's just an example of a solution which, after the fact, appears like a leap.
Right. But it somehow is the only thing that would satisfy
Imagine,
that effect.
the point is that in order to get to the higher frequencies,
Mhm.
you have to have a progressively increasing amount of power to get the oscillations going, to get the oscillations at the higher, or put it this way, to get the oscillations going at the higher frequencies, to get those oscillations more intense, requires proportionally greater amount of power than to get the same intensity at a lower frequency.
Say one more time. See if
Okay. To get the higher frequencies to become more intense, at a higher frequency to get it more intense, requires proportionally greater amount of power. Okay, like for example, here we got this thing, say it's going, its frequency is one rotation per second, okay? And to get it to go from a height of 2 inches to a height of 3 inches, I've got to add a little bit of push to it, say, I don't know, say
something.
1 push, okay, the equivalent of 1 push,
Mm-hmm.
okay? And to get it to go from 3 inches to 4 inches, I have to get it to go, I have to give it 2 pushes, okay? So I can get it more intense by going at 1 push at a time, okay? But if the frequency here were instead of 1 second, say a tenth of a second, so it's going much faster,
Uh-huh.
okay? To get it to go from 2 inches to 3 inches, I got to give it 4 pushes, the equivalent of 4 pushes, just to get it to go up one amount, okay? So in order to get the higher frequencies to be more intense, there has to be a whole lot more power applied to those frequencies, right? Now, that still doesn't need quantized effects.
Then the frequencies are the different colors?
Yeah.
So you want to get,
That still doesn't mean, that in itself doesn't give it quantized effects. That just means that the higher frequencies to get more intense need more power. But what Planck showed is that the specific way in which these frequencies change can only come if they were quantized in the small. Right? That's just a measure, that's a matter of actually looking at the actual data.
right, okay.
Okay?
And does it relate directly to the fact that it's not through a continual increase of the power that you get a corresponding
Right.
continual increase of the intensity of the
Right.
frequency? So the paradox is already there in the experiment.
It's already there in the experiment because you have the light is oscillating at a frequency, but what's happening to the matter? How is the matter oscillating? So Planck says, okay, let's assume the matter is oscillating. And
Right.
that's what's setting the ether into vibration. Okay?
By
But if
matter,
it-
you mean the actual walls of this?
Yeah, little,
body?
little particles in the walls. He doesn't say what they are, but he says, just imagine little tuning forks in there or something.
Okay, and that's actually creating the oscillation, the waves.
In the ether, right? The physics is, he's not saying what's actually physically going on, but he's saying whatever's going on, if light is a wave,
Right.
which I assume it is, and the higher colors are higher frequencies, and then what would account for the fact that as I continuously increase the temperature, the colors and intensities don't continuously change. They change slower and slower and slower and slower and slower, right? And you can make, you can take exponential curves, right? Which start off with takes just a little bit to make it to go, and then in an exponential curve, when you get here, a little bit doesn't get you much height, but over here the same little bit gets you a huge amount of height.
Yeah.
Okay? And that's continuous, right? But the problem is if you tried to come up with a continuous curve that matched what the experiment was, you didn't get there. So Planck did something, but see, that's the way everybody was thinking about it. Planck introduced a new idea into it, which he didn't present as an irony, but which I think is an irony. Which is he said, okay, if this is in thermodynamic equilibrium, then it must have maximized its entropy. And if it's maximized its entropy, it must be the most probable state. So what conditions would this be the most probable outcome? And he said the only way you can get these conditions to be the most probable outcome is if you assumed that, the way he put it was that you have n number of distinguishable oscillators, and they're distinguishable from each other because they're oscillating at different frequencies. M distinguishable oscillators, right? So you've got a big number of oscillators, and they're oscillating at different frequencies, okay? And they're being set in motion by and setting in motion.
What's on the walls?
No, n pieces of energy. And those pieces of energy are all integral multiples of this little h. And the number of, and then if you had that, then if those, then for the high, then you would get this result if it took a greater amount of those pieces of energy for the higher frequencies to be changed, to become more energetic than the lower ones. So he just introduces, sort of like out of the blue, the concept of pieces of energy. You think energy is continuous, right?
Yeah.
Like you're putting, pressure on this cup, and I can increase it by any amount I want, right? I'm just using crude examples of energy, right? The idea of a piece of energy. You can't, there's no, what is a piece of energy? But Planck just says, well, if this is where it was working, you get this result.
Right.
So where he comes up with this idea about a piece of energy, quantized energy, is, if you're looking for a logical, mathematical, you get step A, B, C, D, E, B, and then you're led, inevitably to this discovery of the quanta. It doesn't work that way. The discovery is like Kepler's discovery that there isn't an equant. It's a discontinuous leap.
Right.
And the irony is that he proves that the necessity for this discontinuous leap by saying that by using the second law of thermodynamics to prove that what the second law of thermodynamics doesn't prove what it proved.
Yeah.
That's a little more subtle. I don't know, that's
Yeah.
more difficult to get. But, and I know it's more difficult to get. The only reason why, and you get to the point, obviously, you can refute the second law of thermodynamics, much simpler than what I'm doing here, right? You can refute it very simply, but the way Lynn does it, right? That's the issue here. What I'm trying to do, by looking at it this way, is to look at this question of that the physical universe itself is, that the non-living parts of the universe are also creative. They're not creative like life is creative, but they're still creative. And life is not creative like human life is creative, but it's still creative. And it's like what Kuza says, the lower part, the higher orders the lower, but the lower strives to achieve the higher the best it can.
Yeah, that's funny because it's it's funny because if you are thinking about the second law of thermodynamics, if this state is going to be just the most kind of almost simple state you could possibly have, the most, it doesn't make any sense that.
Well, see, what Planck does is he tries to say, look, the second law of thermodynamics is like a least action principle, right? But the problem with the problem with the second law, the problem with irreversible processes, is it's not. You can't say with the least action principle. I'll give you an example. I actually should have used it earlier. Here's an example he gives. Okay, you think about the least action principle of the idea that geodesic is an idea of a least action principle, right? The shortest distance between 2 points. Okay, so that's determined by the geometry, by the physical geometry. So if you're on a sphere, the shortest distance between 2 points is going to be an arc of a great circle. Okay, so if you have a point on a sphere and you have another point, then there's only one. The least action pathway is completely determined, right?
Unless it's exactly opposite.
Unless they're exactly opposite, unless they're poles.
Right.
Okay? Then the character of the least action curve is determined. It's going to be an arc of a circle, but there's an infinite number of one.
Right.
So all you can say about the one that actually is done is that happened to be the most probable. So then you ask yourself the next question, well, why would that be the most probable as opposed to any of the other infinite ones that were possible?
Mhm.
And then you come up with some explanation, which is what Planck did. If you have these quantized effects and so forth, then this would be the most probable. So the irony is that what turns out to be the most probable is the one that becomes, the one that eliminates, in a sense, probability.
Mhm.
Because if it's the most probable, then you should have an infinite amount of energy possible.
Hmm.
But you don't. You only have particles. You only have certain ones.
Mhm. Right. Huh.
It's like you could say,
Okay.
if you look at the solar system,
Mhm.
you got a spinning plasma disk, and you could get any solar system out of that,
Mhm.
but you don't. You get this one,
Yeah.
and this one, you could say, well, okay, well that just happened to be the most probable of all the possible ones. But this one just happened to be the one that is perfect for life and cognitive life
Mhm.
to not only develop, but be in a position to get out of the solar system.
And therefore, it's not the most random.
So it's not random,
Yeah,
right?
it's not
So
random
in other
at
words,
all.
to say it's the most probable
Mhm.
is just like it's an afterthought, right?
Right. Yeah.
It's like if you throw dice, okay, you have a greater chance of throwing 7 than throwing 2. Because there are, what, 4 ways you can throw 7, but only 1 way you can throw 2.
Right.
But that doesn't mean that if you throw dice 100 times, you're not going to get 2 100 times in a row.
Mhm.
You say it's improbable, but it could happen, right? I mean, it's just, it's just so the point is, if you have something that happens and you try and explain it by probability, it always is after the fact.
Yeah.
Always after it occurred.
Yeah, so what the Copenhagen interpretation does is they say, well, okay, we look at this and we can explain the observed phenomena by constructing a mathematics which says that this result would be the most probable. Therefore, the universe must be completely random, and what you're getting is the most probable. And that's what Einstein and Planck objected to.
Huh. I mean, there's something that's, I read this terrible book from the 90s on chaos theory.
Yeah, well, that's another attempt to do something stupid.
Newton's clock. That was some stuff about the way they calculate the perturbations now. The way they described the chaos theory was that to extrapolate where the planets are going to be through the Newtonian pairwise interactions, including perturbations, how they pull on each other. With all these pairwise interactions, you can only get so precise a measurement now that if you extrapolate so far somewhere in the past, you're going to get off at a certain point. You're not going to be able to know exactly where they are.
Right.
But then they take the step to say that this shows that the solar system's chaotic.
Right.
Because
It's right.
If you mathematics quite accurate enough to...
If you start with the assumption of Newton's pairwise interactions, then these orbits are highly improbable. Every single one of any attempt to do that, you get the Earth flying out of the solar system and Jupiter crashing into the sun after so many years.
Right.
And you can plug that into your computer and stick it into a program, and you can watch Jupiter. It's like global warming. You write certain assumptions into your program, and you say, the planet's going to warm is the most probable outcome. And this is all this stuff, That's the, Planck and Einstein did not draw, they did draw the same conclusion I'm trying to draw from what they're saying, but they didn't say it. They drew the conclusion by the way they reacted to people who went nuts on them. But I think the fundamental issue is the second law of thermodynamics, because that is what reintroduces a idea that the universe ultimately doesn't change. And I think that the existence of quantized effects shows that the universe actually does have the power to change. See, that part of the argument that Einstein, that they objected to was they said to Einstein, well, if you say that you don't agree with the idea that everything is just totally random, then how can there be freedom for new things to happen? Because if everything is totally determined, and Einstein said, no, it doesn't work that way. Because, see, these were creative people who understood how, creativity works. Creativity, a creative discovery by its very nature has to be something which is completely new. Totally from outside what anybody said, what anybody thought, right? Lynn once said, right, science is proving that the way everybody thinks is wrong. He said that to the Russian Academy of Sciences. And so creative discovery by its very nature is something that is completely outside the existing domain of thinking. But there has to be something in the existing, there has to be a potential within the existing domain of thinking to change itself in a fundamental way. So yes, it's something that, so if all you have is randomness, then how can you get something that's totally new? Or let's put it this way, if you say the universe is fundamentally random, then creative discoveries is simply the improbable happening. And you're saying that creativity is simply, it's creativity I'll make it even more absurd. Human progress depends on creativity. Creativity is nothing more than the highly improbable thing happening. Therefore, human progress depends on the most improbable thing happening. But in truth, when you look at the nature of human beings, the most probable thing for human beings to do is to make creative discoveries. Because that's in our nature. That's what we do when we're babies. We keep changing the way we're thinking by making new discoveries. So human beings are, the most probable thing for a human being to do is to change the way he or she is thinking.